Hello and welcome. Firstly, I just want to say that I hope everyone out there is staying healthy. And I'd also like to say that if the title of this talk doesn't look familiar to you, you might have clicked on the wrong link. We are generally happy for people to capture or record elements of this course, but please be respectful if individual contributors ask you not to do so during their respective sections. There is contact info at the end of this introduction should you wish to reach out to us to give us feedback or request course notes. A little bit about this course. I'm fortunate enough that my career, my passions, and SIGGRAPH all sort of have intertwined over the years. And my first SIGGRAPH was 2001, and I spent the entire time on the exhibits floor holding together the latest distributed composited rendering tech from Silicon Graphics, where I was working at the time. But what I did see ignited my imagination, and I not only came back for more, but was ultimately driven to volunteer for the conference a number of times. Specifically, I was motivated to serve as mobile chair for the conference by all of the amazing work going on in the mobile industry that I thought that the SIGGRAPH community seemed woefully unaware of. This course hopefully highlights some of that work and raises that awareness. And there is always more work to be done in this space. The promise and importance of mobile technology is such that The Economist in 2015 chose to call the smartphone the defining technology of the age. Now, I'd argue it's not really a single technology. There are keystone technologies that enable a device to run untethered to a power supply, but it's really the product of years of effort in a huge industry, including logistics, new types of stores, and new business models. A raft of industries now sit on top of all of this. And I think it's a good reminder that when we say technology, we really mean sometimes that technology and business are shifting together. To get a sense of the scale of what we're talking about, I think it's interesting to compare phones to humans in terms of the population. So last year, the mobile industry shipped about 1.5 billion smartphones, and we can expect to cross the 10 billion units shipped in this total in this year. Sam tells me ARM ships over 1 billion GPUs a year at this point, and that's just one vendor. There are a few other industries that compare to this global scale. The industry is broadly projected to continue to grow and saturate at around 2 billion units a year. Of course, no one knows what COVID-19 will do to that yet, but initially suggestions are that people are focused more on mobile technology right now than ever before, and we're certainly seeing that in the game space. Compare this to the human population. In 2019, World Bank estimated 7.7 billion people, of which 3/4 are 15 years or older. The global birth rate was around 140 million people a year, so that means that each year we make very close to 10 times the number of phones as we do people. So where do all those smartphones go? Well, 1/3 of the world population owns a smartphone. But this percentage is much higher in developed countries. The US is about 80%, the UK is about 75%, and South Korea is very close to 100%, north of 90% at any rate. And so overall, the worldwide average is 90% of people own a phone-like device, whether it's actually a phone or not, but we're talking just phones here. This is a market that's limited only by world population and the ability of those people to be able to purchase phones. Successful advances in graphics technologies that are applicable to mobile will be felt by hundreds of millions of people. Advances that are cost effective will be felt across the globe. Even at this scale, there is room for growth. I say only 1/3 of the population owns a phone, whereas by these numbers, 3/4 of the world could own one. And for any of you that have young teenagers, you might argue that the number should be lower than 15 to think about this demographic. Here we see an overview of what you might call a typical premium SoC. A bit of a disclaimer, this diagram doesn't necessarily describe a specific SoC out on the market, but is meant to be reflective of a top-tier device. When we look at the features here, it's pretty astounding. Again, we talk about number of CPU cores. It's a bit woolly because not all cores are equivalent. Things like the big little architecture from ARM, where you have power efficient and performance efficient cores on the same chip, and now some of the newer tri-cluster designs where you have sort of 3 different optimization levels on the same SoC. Similar for GPUs, not all cores are created equal, and so talking about GPU cores is mostly meaningful when you talk about sort of 2 different layouts of the same GPU from the same vendor. So if you say there's an 8-core version on one SoC and a 12-core version on another SoC, you can kind of think about that. But while most of these chips are used for smartphones, the SoCs and the smartphone OSs that run on them are capable, very capable computing devices in general. What's pictured here would have run circles around the graphics workstations I worked on at Silicon Graphics, for example. I'd also, just as a side note, the memory block here just strictly talks about the bandwidth that's available on the SoC. The DRAM is actually attached externally, but for this configuration would be about 8 gigabytes typically. So the agenda for the rest of what we're going to have here is going to start with myself giving you a little bit of a primer on mobile graphics and mobile GPUs. Then Jose Emilio from ARM will tell us a bit about efficient use of the Vulkan API for mobile. Next, Kei Chang will talk about optimized deferred shading. After that, Arseny is going to cover large voxel landscapes on mobile. And last but not least, Romain is going to talk about high fidelity rendering for mobile. I'd like to thank in advance all of our speakers. Thanks, of course, to the SIGGRAPH committee for having us here, and thanks to all of you for attending. I'd really like to encourage all of you to give us feedback. You can see the contact information there, and if you want to download the course notes, they're available at this URL. We really do appreciate the feedback. We try to offer this course every couple of years, and your feedback really helps make the updates fresh. So first up is myself, and I'll be giving you, as I say, a little context to set the tone and the stage for what everybody else will be talking about afterwards. Okay, so let's have a quick introduction into mobile graphics and mobile GPUs. We're going to start off with a quick definition of what we mean by mobile, just to have a baseline for what follows. After that, we're going to look at a few of the key factors that constrain not just graphics execution on these devices, but other bits of hardware as well. Then we're going to have a high-level overview of GPU approaches and why mobiles tend to favor a particular approach, and there may be some hints along the way that will that you may pick up as we have this discussion. And finally, we'll touch on a few tips and gotchas when analyzing the software you're running on these devices. So for the purposes of this talk, and at least from my perspective, indeed this course, I'm avoiding the sort of mobile versus desktop dichotomy that I think people tend to kind of gravitate towards in this setting. For the purposes of what we're here for, we're talking about a phone-like device. It could be a tablet or what have you. And the lists here that you see for the sort of mobile and non-mobile, these are just endpoints of a spectrum. There are a myriad of devices that fall well in between either of these endpoints. And this is a landscape that's evolving all the time. So for me, mobile primarily is about thermals, power, and size, actually. So for example, your favorite PC graphics card GPU is several times the size of the SoC inside your phone. It could be more than several, but anyway, a device may use the mobile SoC, but if it has a tethered power supply, if it has a fan or some other active cooling mechanism, I would argue that it's no longer mobile in that sense. Certainly, many of the considerations for writing software that's supposed to run efficiently on those may apply. There may also be some quirks. So, for example, you may have this SOC that's in an embedded environment that doesn't support virtual memory or doesn't support dynamically allocated memory or something like this. So we're not talking about that. These are sort of general purpose phone OSs and the like. So on the topic of thermals, this is the sort of key governing factor for all mobiles. Every bit of active silicon in the SoC, as well as other active sort of devices or processors or whatever on the system board of your phone device, generates heat. That's just how computers work. It's also the case that computers don't really like heat. They tend to kind of shut down or melt in some circumstances. If you've ever put your phone down on a hot day outside, you may notice that your phone has turned itself off because it got too hot. Phones and tablets are limited to passive cooling. In other words, whatever heat the device is capable of dissipating just sitting there is how much thermal behavior you can tolerate. That's how hot the device can be and still operate normally and comfortably. Tethered systems, on the other hand, are able to run fans and possibly liquid cooling systems in the case of some high-end gaming rigs in order to address these thermal limits. And so they effectively don't have this problem. Mobile devices, again, relying on the passive cooling, they have to constantly monitor these thermal conditions, and they have to then adjust the voltage and frequency of various portions of the chips that are either too hot or drawing too much power. This can, of course, have a huge impact on the behavior and performance of the software on the device. For example, if your CPU is all of a sudden running at half the clock rate that it was running at a moment ago, a lot of your performance goes out the window. And certainly, to that point, we all know that CPUs and GPUs and other sort of execution units in the system to draw power in order to operate. But the real culprit, as far as I'm concerned, is memory. Okay, remember all those devices inside an SoC that we talked about during the introduction. Here's a slightly different representation of that. All of these things, the radios, the sensors, the accelerators, and so on, they all require memory in order to do anything useful. Talking about memory is confusing. People, for example, will refer to quantity. How much memory do I have? I have 64 gigabytes of RAM or whatever. But that doesn't really tell you how useful the memory is. So for example, if you had that 64 gigabytes of RAM, but it was only connected to an 8-bit bus running at 1 megahertz, that doesn't really give you very useful access to that quantity of memory. So you have to consider other aspects. And to that end, I would argue that memory is the single most expensive resource on a mobile device, and I'm including lighting up the display in that. When you think about the fact that dynamic memory must constantly be refreshed in order to preserve its contents, you're constantly powering any dynamic memory in your system. So the more you use, the more power you take, and the more heat you generate. Configuration of memory varies pretty greatly based on system architecture. So your phone may have different things than a more special purpose device, like a standalone VR headset, something like that. But what you'll see basically is in mobiles you tend to have what's called a unified or shared memory configuration, where you have one pool of memory physical memory for the entire system. You may there are some systems that have dedicated memory, so the GPU has its own block of memory that it only has access to, and there may be some splits. So you may have something that's fundamentally a unified memory setup, but maybe a portion of it's carved out for the CPU and a portion of it's carved out for the GPU, and actually the bandwidth can work that way as well. And systems may employ specialized memory types for particular use cases. So there are memories that are specifically optimized for usage by GPUs, things like GDDR memories. And then there are lower power memories that are typically employed, again, for mobile. They're not restricted to that, but that's typically what they're developed for. So here's, as it says, very, very rough comparison. Just as a note here, These numbers don't describe a single device in each category, but represent a rough overview of what you could expect from the latest generation of devices from across this spectrum. And these numbers, they're rounded, they're ish, but they do come from SOC specifications, GPU vendor specifications, and device review sites like Tom's Hardware and AnonTech. So you can go employ your favorite search engine and find all these numbers. They're pretty close to what I'm representing here, but take the tilde with a grain of salt. So at this sort of high end of things, discrete GPUs targeted at tethered systems have lots of local or dedicated memory. So they'll have literally on the graphics card, the graphics RAM is there just for the GPU, and it doesn't have to go, traffic doesn't have to go across the system bus for that. It just has a very high performance local bus that provides the GPU with all its bandwidth. Mobile GPUs, by sharp contrast, share a much smaller amount of memory, as you can see, and they also share a much smaller pipe, a much lower amount of shared bandwidth in a typically unified memory architecture. Now, as I mentioned, in some cases there might be a split. So again, you might have an explicit carve out where the GPU is guaranteed a certain amount of memory and guaranteed a certain amount of bandwidth, and the rest is designated for the rest of the system. And in the middle, you have consoles, which are kind of like a special purpose PC, really. And they do fall somewhere in the middle. They have, sort of bandwidth numbers that are similar to PC bandwidth, but, the physical quantity of memory may be quite a bit lower than that. But again, you're going to have, something kind of in the middle there. It's easy to get trapped up in these sort of raw hardware specification numbers, thus the comment on specsmanship. The available memory footprint and bandwidth that you'll experience at runtime are significantly reduced over this for reasons like, again, power, thermals, other system overhead, and even in some cases the types of actual memory chips that are connected to the memory controllers. So. Now we're going to look at how GPUs actually approach work. We're not doing a deep dive here, so I won't be covering low-level implementation details for a specific vendor architecture. Every vendor's hardware is different, and indeed each generation or architecture is likely different from its predecessor, or even from sort of a sibling chip within the same generation. This is just intended to give you a basic grounding in how GPUs work. So the image here is the scene we're going to use for the purposes of this sort of walkthrough. And note the two basic approaches here, because we're going to cover those now. So this is a very oversimplified diagram of what an immediate mode rendering GPU looks like. The big green block is the GPU silicon. The blue block is the RAM that the GPU has access to. And so, as you kind of see, based on the direction of the arrows, the geometry data is stored in some buffer in RAM, pulled into, fetched onto the GPU, where the vertex shader transforms the positional information into screen space, and then those, maybe does some other work, stores some intermediate data back out to RAM. The rasterizer then interpolates all that data across the screen space form of the primitive, and issues jobs so that the fragments all get shaded, and those go out as they're processed out to the in-memory render target in RAM. So each triangle is just processed all the way through the pipeline, and then the next triangle, and then the next, and so on. And so that whole scene that we just looked at all goes through the pipeline sort of in order like that. And as you can maybe see, this is very memory intensive. You may have to, triangles that overlap, for example, may get drawn twice, and so on. But these platforms tend to have bandwidth to spare, so maybe that's okay. Now, when we talk about tile-based GPUs, real quick, we should say this is what we mean. So tiling is just basically each render target is divided into a rectangular grid of what we're calling tiles. So just an area of sort of a rectangular area of pixels. And let's now look at why that's significant to mobile GPUs. So again, very simplified diagram of a tile-based GPU. And again, how this really gets done, very vendor specific. Same relationship, so the green is GPU, the blue is RAM. And the first part is very similar. So the vertex shader starts to do the processing based on the fetch data from the buffer, and it transforms all the geometry into screen space. But rather than going directly to the rasterizer, you'll notice there's a block in the middle labeled tiling unit in this diagram. And what the tiling unit does is actually sorts all of the triangles, all these primitives, into bins. There's one bin per tile of screen space. So that grid we saw on the last slide, each one of those tiles would basically be sorted into this bin, and it would just list all the triangles that overlap that particular tile of the screen. This is sort of the key piece. What this means is that all of the scene data is processed, all the geometry is processed well before we ever get to the rasterization and fragment stages. And so because of that, we're able to make some decisions about whether or not it's even necessary to sort of shade a particular triangle, because it might be way in the back. But anyway, once all the geometry has been binned, each bin is sent to the rasterizer and sent off for fragment shading. Now, the other block of interest here is the one that's labeled tile memory, and the key thing here is that is where the actual work is done. So that tile memory is very fast on-chip memory. It's not cache memory. It's part of the GPU, and it's where the fragment shader actually does all of its work. So that memory has to be big enough to store multiple multi-sampled render targets, including depth and stencil, and the size of the actual tile. So how big the tile is in pixels is sort of adjusted to make sure that there's enough space in there to actually do all of that for a given tile. And one of the upshots of that is that you don't actually have to allocate, if you don't need, say, the depth buffer for anything else, you don't have to allocate an actual in-memory depth buffer. You don't have to actually allocate an in-memory multi-sampled anti-aliasing color buffer. All you need is the output that you care about. So you need however many single sample color outputs, and that's it. So it saves a tremendous amount of memory. And because all of the work is done in the tile memory, you're only ever writing out the final results that are going to the render target. You don't have to read anything back in and write it back out again afterwards, the way that you might in the immediate mode rendering case. And because of this, because we know a lot about the geometry, as I say, from this sort of early binning process, there are a series of early depth tests that can be done sort of prior to rasterization, and those enable certain optimizations at the hardware level. So, for example, there's one called forward pixel kill, which basically can remove a fragment that's already made it down into the queue. But because the realization comes that's going to be overwritten, it just gets yanked out of the queue, so it never gets processed any further than that. Another technique is called hidden surface removal, which is sort of the converse of that. So based on similar early depth results, in this case, the fragment just never gets issued in that case, and rather than killing it after it's already been issued. So I mention these here because they're hardware optimizations that you, as the programmer, sort of don't really have any control over. But software optimizations that you can do is what we're going to move on to now. So Platform and vendor tools are your friend. Furthermore, if you happen to be using a game development environment, so for example, the image here is a capture from Unity's timeline profiler that I did while working on a project. And as you can see, it shows you a tremendous amount of information about what's going on. You know, how much rendering work is going on, where in some cases where the stacks are the deepest. But this is fundamentally cross-platform. Something like a game engine is a fundamentally cross-platform piece of software. So there will be some platform-specific considerations that you won't necessarily be able to unravel through this view. So there are platform-specific tools if you're targeting iOS, if you're targeting Android. There are tools for those platforms that will show you quite a lot more. And then even deeper, there are tools that come directly from the GPU vendors that you may be able to use to get a really much more deeper view of your workloads. And you should definitely become familiar with those. They'll help you out quite a lot. So from a high-level perspective, there's some optimizations that we can talk about here that will help you out. So in the area of texture compression, we have I will say compact texture encodings are definitely your friend. And if you're using things like, let's say, RGBM encodings for light maps or octahedral encodings for normal maps, you still want to compress them if you can at all. And certainly any other textures that you're streaming in from disk, you want to compress all those to be compressed as much as possible. The bandwidth savings here is huge. Sometimes 2 to 1, 4 to 1, 8 to 1 possibly. The downside is, again, it's a cross-platform consideration. Different platforms support different formats in some cases. I will say, so ETC2 is pretty universal across everything. And ASTC is getting pretty universal as well. And ASTC now also has much more prevalent support for some of the high dynamic range compression formats, which makes that really, really interesting looking forward. With respect to data representation, I definitely recommend you try to use lower precision data types where you can. So for example, 16-bit floating point rather than 32-bit, or even smaller integer formats wherever possible. So you can save both memory footprint and bandwidth by providing buffer data or even outputting buffer data in those formats. The savings is direct in terms of memory footprint and bandwidth. And also, though, within your shaders, declaring your operands in lower precision, if the math will stand up to it, you can often get significant ALU gains by operating on the lower precision data on a mobile GPU. Reduced precision does come with some drawbacks. For example, you may experience limited texture addressability. The FP16 is only capable of representing a certain range of numbers, and also the math the arithmetic can explode on you, and you can get results like nans or infinities or whatnot. And so you have to be careful with optimizations like this. Though there are some sort of debug logic that you can use in shaders to do things like either eliminate nans, clamp them, or whatever, or at least to identify them. And then in terms of screen resolution, I will say the resolution on some of these devices is insane. So pretty much never render at native device resolution. You're fundamentally outputting to a small, probably smudged screen, and you're likely not to notice the difference. Some devices have a small enough native resolution, but if you're rendering at like QHD+, you're asking way too much out of your CPU, GPU, and memory system. So what you want to do is render your UI at full resolution, render your game content or whatever at fractional resolution. You of course have to test to make sure that what you're getting looks acceptable, but you upscale that main content and composite it with the full resolution UI, and you'll get really great results that way. And in some cases, the platform actually has hardware to do this for you rather than you doing it in a shader composition. One important note that I'll mention here, when you're analyzing and optimizing graphics applications especially on tile-based GPUs, per draw statistics are nearly impossible to obtain at all due to the way that we've seen the draws are processed. Some of the vendor or platform tools can help with this, but those are still likely to be synthetic approximations in some cases. So, for example, the replay part of your capture and replay in the tool may or may not actually replicate your clock state and your voltage state, for example, from when the capture was taken. So it's really important when you're doing these optimizations that you're not only looking at this in a frame debugger and a shader debugger, but you're also looking at a live timeline analysis of this, either the one that you see here or one that's available in your set of platform or vendor tools. And that's it. So thank you very much for your attention. Next up, Jose Emilio Munoz Lopez will tell us about how to efficiently leverage the Vulkan API for mobile platforms. After completing a master's degree in electronics and computer science at the University of Edinburgh, Jose Emilio joined ARM to work on the Mali family of GPUs. Initially, he was involved in their driver development and instrumentation tools, and 2 years later, he had the opportunity to take his passion for computer graphics to a new level at the graphics and gaming team. For the past 3 years, he has been working with Vulkan both internally and at multiple collaborations with game developers and ecosystem partners to find ways of achieving the best visual fidelity at maximum performance on mobile. Please welcome Jose Emilio.
Hi, I'm Jose Emilio. I'm going to talk about Vulkan and some of our best practices for mobile. As you know, Vulkan can be quite a powerful yet complex API, and I hope today's presentation will help clarify some of the main questions around it. I'll start by introducing the project that we have been working on most recently, known as the Vulkan Samples, and then I will take you through 3 of these samples, from the best practice recommendation to what the sample does and the results, and then close with a brief overview of the framework behind all of these samples and some further work and resources. The motivation behind the Vulkan Samples project was our best practice guide. This is a collection of do's and don'ts around graphics rendering, both using OpenGLES and Vulkan. And it is the result of many years of optimization of our hardware and software, and also by using and also optimizing and helping profile applications from game developers. Now, this set of recommendations we thought would be useful to also have some experiments, both for us and the community, to show the real impact of the different ways of achieving something in Vulkan. And that's why we introduced the Vulkan Samples. The Vulkan Samples try to isolate each of these best practice recommendations and help you experiment with them. And when you toggle different options, you can directly see the impact they have in real time, because the renderer will also display some real-time hardware counters. Now, these samples were donated to Khronos and is now in the Khronos Unified Samples repository, which is accepting samples from not just us, but also other vendors and also independent developers. And it's a very valuable resource when you're learning Vulkan or when you want to take your a Vulkan application to the next step. And this is how they look like. So a given sample will always show some scene, and at the bottom we have some options that you can toggle with and experiment with, and then see the impact that they have on performance. And as I said, you can actually measure this impact because you have different values for different hardware counters that you want to trace in this particular case. This is something that you can configure as well. And with that, every sample also has a tutorial. And the tutorial will take you through the theory behind the sample, also through the different configurations that it offers, and at the end, a summary of the do's and don'ts from our guide, as well as some help in profiling the sample or your own application to look for this particular recommendation using the ecosystem tools. The samples also offer a number of scenes. So here you see Sponsa, but we also have another couple of scenes that we developed in-house, like this one and this one. And you can use any other scene that you want as long as it's specified in the GLTF format. Our samples are based around performance, always looking for ways to optimize the performance in a Vulkan application, and in particular around the concept of bandwidth, because it's one of the main limitations on mobile. So to set the scene, you're probably already familiar with the graphics pipeline. We're going to be focusing on render passes, and for that we need to look at the vertex and fragment processing stages. So for a simple scene, we know that we have our geometry, and once it's transformed, it will be rasterized, and then we have to work with attachments. In this case, we have a depth attachment and a color attachment for doing the fragment processing. Now, this collection of attachments and operations that we carry out is what is known in Vulkan as a render pass. And render passes can consist of one or more subpasses. Here, another thing that we specify in Vulkan is for each of these attachments, what we're going to do before the render pass and after the render pass. And these are known as load and store operations. These load and store operations are specified for each attachment. And what we're saying here is what we want to do with that attachment at the beginning of the render pass and at the end. Before we go into more detail than that, I also wanted to illustrate the differences between an immediate mode GPU and what we usually find on mobile. In an immediate mode GPU, very simply put, we are loading the geometry, and then in a queue, we are taking that geometry, we are rasterizing the scene, and then we are processing all the pixels at any rate that is necessary. So for every pixel, we are writing to memory or reading from main memory as much as necessary to render the scene. And these arrows here at the bottom, they illustrate some operations that are very expensive and require a lot of bandwidth. So on mobile, we're going to try to minimize this reading to and writing to memory. And we do that by moving all the fragment processing to the GPU into something that is known as tile local memory. This is achieved by subdividing the screen into tiles. So a tile is simply put a collection of pixels, a subdivision of pixels in the screen. And what we do with that is that the GPU can render a tile at a time. And that means that for rendering a particular fragment, we don't need to go all the way to main memory. We can keep everything that we need for a given tile in tile local memory in the GPU. This memory is much faster and much cheaper. And as you can see here, at the end, we have a single transaction to main memory, or a single store operation, that is to write out the final value of the samples in the tile. So now we're talking about loading from main memory and storing to main memory. Those are the load and store operations that we specify in the render pass. The options for load operations are load, clear, and don't care. When we say load, we are asking to read from main memory, which, as we said, is expensive and requires a lot of bandwidth. If we can avoid it, we recommend always specifying the attachment load operation to clear or don't care. Clear in tile-based renderers means that the tile will have been first cleared to a clear color, and then we can render on that. Now, for a tile, this is a cheap operation, but if you want to save this clear color to main memory, you will be using something known as VK command clear attachments. But this is very expensive and usually not needed, because when you are starting rendering a frame, usually the previous contents of the frame are not needed. So we can optimize this, and by specifying load up clear or load up don't care, we are avoiding having to read the previous contents of the frame buffer to the GPU. Similarly, for store operations, usually by store we mean writing to main memory, and this is also something that we want to avoid as much as possible. For attachments like color, if we are presenting the final color to the screen, we will need to store it. But for other attachments like depth, once we are done rendering, usually the depth attachment is no longer required. So in this case, we can use store up don't care and avoid writing it out to main memory. In our diagram, that means that if we are rendering our tile, we are doing the depth testing directly on the tile. So that means that our depth attachment can live entirely in tile local memory. There is no need to read the previous contents of the depth, so we can use a load up clear or don't care. And there is no need to write out to main memory the depth once we're done rendering. Once we're done rendering, we can just write out the color and leave all the depth values in the tile local memory. And this is something that we can specify clearly and upfront using the Vulkan API. To do that, we need to, as you said, use the right load and store operations, but there is also another couple of things. There is a flag for the attachment that is to say that the attachment is transient, and this means that the attachment will not even require any memory in the main memory. It will temporarily live only in local memory. And to do that as well, we need to, when we are allocating the memory for this attachment, we need to specify the lazily allocated bit. And in our sample, you can see that if you toggle between load up clear and store up don't care, and you will see in the bandwidth counters for read and write operations that there is a significant improvement in bandwidth if we make this depth attachment transient. Everything that we can save in bandwidth means that we can save in power, and on mobile that always translates to a better user experience. Another example of where we can save bandwidth is when using something known as multisample and Helis. But before going into the best practice, I'm going to do a quick recap of what multisample and aliasing is. In our scene here, you can see that there is some artifacts around the edges of the models, and these are basically the result of trying to take an infinitely detailed scene and sampling it, converting it to a discrete space, such as the screen space. So to avoid this, there are some techniques that blur out the edges and make them look much nicer. And here you can see them side by side. But how does multisample anti-aliasing work? Well, without anti-aliasing, what we're doing when we're rasterizing the polygon, in this case this triangle, we're looking at the center of the pixels. And if the center lies within the triangle, then we are rendering it as part of the triangle. By that I mean, we're taking these pixels, and then for each pixel, we are computing the result of the fragment shader and saving it to the pixels. But as you can see, this creates around the edges like big jumps or this staircase effect that is what translates into the jagged edges. In contrast, if we do multisample anti-aliasing, rather than just looking at the center of the pixel, we're defining a set of samples. In this case, we have 4 samples per pixel. And then we are checking for each sample if they lie within the polygon. If they do, we are rasterizing the pixel. I mean, we don't need to just check for the center of the pixel. We are checking for all the samples. And if any one of them is inside the polygon, then it will contribute toward the color of that polygon will contribute to the color of the pixel. And that means that then we have to still run the fragment shader only once. We're not increasing on our fragment cycles because we're still running only once, computing the color for the center of the pixel, but we're saving it to a number of samples. So as you can see here, for the samples inside the polygon, all the samples will receive the same value. But for the pixels around the edges, we will have anything between 1 and 3 samples that will have the color of the polygon saved to them. And that means that then we are when we are averaging the values of all the samples, we will have a gradient or a much smoother transition between the color of the polygon and the color of the background. And this is what smoothes out the edges. Now, when I said that we average the results of the samples, this is the operation known as the resolve operation. We are resolving the samples from 4 samples, which we are using to get more information and get a smoother result, where we have to reduce all those 4 samples into 1 sample, because at the end of the day, when we're rendering to the screen, we need 1 final color value. And this operation, as I said, is known as the resolve operation. To efficiently resolve the multisample attachment, in Vulkan you have 2 options. But the most efficient option is to specify it upfront when you are defining the render pass. And this is a parameter known as p-resolve attachments. If you specify upfront what attachment is going to be the destination of the resolve operation, you, as we're going to see in a second, you will be saving a lot of bandwidth. If in contrast you use the vk command resolve image, you will be introducing a lot of extra overhead. We're going to see why. In our tile GPU, this means that our multi-sample attachment can also be transient. So similarly to the depth, the multi-sample attachment, the 4 samples that we have to use per pixel can stay always in tile local memory, and we only need to write out to main memory the final resolved color. In a more simplified way, you can see here we have our scene render pass using multi-sample depth and color. And when we are done rendering the tile, we are writing out to main memory only the final single sample value. And this is achieved by specifying it up front with pre-resolve attachments. If in contrast we are using vk command resolve image, what we are implicitly specifying is that the GPU should save all the samples for every pixel, so the 4 times the size multi-sample attachment to main memory, and then reading it back to the GPU in order to carry out the resolve operation. And as you can see, this is very wasteful and expensive. In our sample, as you can see here, the depth stays transient because it's not required. But in our sample, we also add the option to resolve the depth. To resolve the depth, you need to use an extension that has been introduced in Vulkan 1.2 as part of the core spec. And with that, you can resolve the depth. Now, what will you want to resolve the depth? So we have here a post-processing render pass. We need a separate render pass because for this particular post-processing effect, we are accessing the pixels, the neighbor pixels. So that means we cannot use subpasses. And then we are using both the depth and the color to carry out this specific effect. But in this case, again, we don't need to write out all the samples, the multi-sample attachments. We can simply write out to main memory the single sample attachments and then reading this back in for the post-processing render pass. And all of this comes together in our sample. We start with no MSAA, and then we have several options. We enable 4x MSAA. This barely has any impact in performance because it's quite optimized. But then as soon as we switch to vk command resolve image, as you can see in the values for external and read and write bytes, there is a considerable difference in bandwidth between resolving on tile or resolving in a separate render pass. The sample also gives you the option, as we're enabling now, to do post-processing, and then when we do post-processing, we can again toggle between efficiently resolving the depth attachment or not resolving it. For the third and final sample, we're going to talk about synchronization. As we saw in this case, when we have multiple render passes and there is a dependency between them, we need to worry about how to synchronize the work between the 2 render passes. And that in Vulkan is done through several mechanisms, but today we're going to talk about pipeline barriers. Pipeline barriers work with pipeline stages. Pipeline stages are defined in this Vulkan enumeration, and for our example, we're only going to consider this view. Let's map them to the original graphics pipeline that I showed earlier. First, commands will go through the top of pipe stage. That will be followed by the geometry stages, and after rasterization, the fragment stages, ending with the bottom of pipe stage. Every command we submit to a queue will go through these stages, and the top is just a way of signaling that a command has been parsed. A bottom of pipe is also a helper stage to signal that the command has been retired. When we submit commands to a queue, they may execute out of order. In fact, they may execute out of order between command buffers or even queue submissions. So what we do is we have to synchronize this work, but we do that through synchronizing the work in these stages, not for individual commands. This is how a pipeline barrier looks like. With a pipeline barrier, we are effectively dividing the command stream into parts and specifying that all commands after the barrier must wait at a certain destination stage until all commands before the barrier have reached a particular source stage. To visualize this, consider this timeline where we have a CPU submitting work to a GPU, and in the case of Mali and other GPUs, this work in the GPU can execute the vertex and fragment work in parallel in 2 separate slots. Here we are color coding the render passes, so you can see that for every render pass we have some work that is going to the vertex and some work is going to the fragment. We are adding a barrier between every render pass, and this barrier has a destination stage of top of pipe and a source stage of bottom of pipe. This means that all the work that we submit after the barrier must wait at the beginning of the pipeline. That is, it must not do anything until all the commands before the barrier have reached the bottom of pipe stage. That is, until they have reached the end of the pipeline. So this means that nothing from the second render pass may execute until everything from the first render pass has completed. And this is introducing these big gaps between the render passes, or bubbles, which is very inefficient. Compare that to this other barrier. The change is very simple. We're basically saying that in the second render pass, we only need to wait for the fragment work from the previous render pass to complete. So this means that the vertex work from the second render pass can execute in parallel to the fragment work from the previous render pass. And this way we completely avoid the bubbles and maximize the throughput. To visualize this in our sample, we can see that in the vertex and fragment cycles that there is no work from the vertex and fragment happening in parallel. Anytime there is vertex work, there is no fragment, and vice versa. If we overlay those timeline diagrams that we saw, it will look something like this. This is for the bottom to pipe barrier. Compare that to the fragment to fragment barrier. As you can see in this case now, the vertex almost always executes in parallel to the fragment. In terms of performance, in this case, because it's a very simple scene, there is no difference, and also we are vsync bound, so we're already at 60 FPS. But in real games that are GPU bound, we have seen that just a simple change to a barrier has increased performance by more than 56%. And that's all the samples I wanted to talk about. Now I'm going to do a quick recap of our framework. The framework is behind all the samples. It is cross-platform, so that allows you to debug on desktop and run and profile on mobile, for example. It offers the right level of abstraction so that it makes the API easier to use while still giving you flexibility to experiment with the API. And it also incorporates certain utilities like SPREVy cross that automatically generates some objects based on the shader, inputs and outputs, and a GLTF loader, so you can use your own scenes. These are all the samples that we have there today. And apart from new samples, we are also considering, we are using the framework as a way of modular parts so that some of them can be used as a standalone libraries. We're working on that. We're also using the framework to investigate other techniques like efficient lighting techniques or post-processing effects. And finally, we're also integrating the LunarG best practice object from the validation layers. And with this, what we want to do is make sure that all of best practice and all the samples recommendations are present in that layer. That's a layer that will automatically check if you're following the best practice. And we can also test it with the samples. This has some useful resources that go all the way from introduction to Vulkan to some of the more complex topics like synchronization. And that's all from me. Thank you very much for your attention, and I hope you check out the samples. We welcome feedback and contributions. Cheers.
Next up, Kei Chang will tell us about the deferred shading path in Unity's Universal Render Pipeline. Kei Chang is a console R&D engineer working at Unity. He's been in the video games industry for 15 years and honed his skills as a graphics programmer, working on several AAA games spanning a large variety of game consoles. Prior to Unity, he worked at Square Enix, where he was actively involved in the development of Final Fantasy XV graphics engine and responsible for many graphical features used in the game. Please welcome Kei Chang.
Hello there. So I will talk about the deferred shading techniques in the Unity Universal Render Pipeline. So first we have a disclaimer about recording policy. So my name is Kei Chang and I'm a senior software engineer specialized in graphics. I'm located in Vancouver, Canada, and I'm working for Unity Technologies. So I've been working in the video game industry for more than 14 years, and I ship games on all major consoles. And obviously I specialize in graphics rendering. And my main experience is actually developing game and engine on console hardware. At Unity, I'm currently mainly working with Nintendo Switch. So our agenda is first I'll talk about the universal render pipeline and what it is. I talk about some platform considerations regarding how to implement the FUD renderer in the universal render pipeline. I briefly explain the stencil-based deflated shading technique as opposed to the tile-based deflated shading technique. And then I will show some performance results we have on both PCs and mobile hardwares. And finally, moving forward, I talk about the future work still required with the deflated renderer. So first, let me show you this quick demo about the deflated renderer working in universal render pipeline. So it's just 40-point light dynamically moving. So that demo will not be implementable using a forward renderer because it's limited to 8 lights per mesh. So the universal render pipeline. So historically, the way Unity perform rendering has been through the built-in render pipeline, which is in essence opaque C++ code. So it was difficult for users to use and to customize because obviously if you didn't have access to the source code, you had to kind of reverse engineer, figure out how things work. So that was quite difficult. So instead, Unity developed the scriptable render pipeline that we call SRP. And that's a C# API that exposes a lot of graphics features. So you can create your own command buffer, and then you have some high-level functions to render meshes, specific material, or with specific shader variant, and so on. So basically, it allows users to write their own render pipeline in C#. And so Unity is also developing 2 out-of-the-box implementation that actually use SRP. The first one is HDRP, High Definition Render Pipeline, and it's targeted toward high-end platforms like PlayStation 4, Xbox One, HD consoles, or high-end PCs. And then we have the URP, or Universal Render Pipeline. And so that's a pipeline that is designed to run on all hardware, all platforms that Unity supports. So URP is the future Unity replacement for the built-in render pipeline. And so since most of the code is in C# land, users can actually look at the code, customize the render pipeline to fit the need of their game. The source code is hosted on GitHub, and so actually, again, you are able to actually just download the repository, clone it, and make your own branch. And then, or you can also see actually the latest development for URP. And so the default renderer is actually a branch inside the universal render pipeline. So URP is not yet at parity with the built-in pipeline, so it's missing a few features. One of them is the default renderer, but it's also missing decals, point light shadows, a big lighting mode, reflection probes, some reflection probes, separate light layers, HDRP style, for instance. So there's a bunch of people now working to get that feature parity, and so we are aiming for 2021, where the users then can have a seamless experience moving from built-in to URP. So deflated shading is a very broad technique. There are several possible implementations, but the 2 main implementations are stencil-based or tile-based. So stencil just render the light shape into stencil buffer, whereas the tile-based default shading approach actually classify light into screen space tiles and then render the tiles using complete shaders. So it's very popular right now with desktop GPUs and home consoles. Also, URP must run on large set of platforms, from very low-end mobile device to very high-end devices, home consoles. And so there's a very wide spectrum of devices. And so if you want to implement a technique that runs on all those platforms, actually, we concluded that actually you cannot have one solution that just works on everything very, at the best optimal capabilities of the device. So instead, we have to implement several solutions for each platform. So let's talk about platform considerations. So what are our platform constraints? So our mobile GPUs, which is your phone, your tablet, they do have, actually, a lot of them now have a hardware, a GPU that supports tile-based default architecture. So that's a hardware architecture. They have very low fill rate, so you cannot do a lot of overdraw, expensive arithmetic operations. You have to be very careful on the complexity of your shaders because it easily has an effect on your frame rate. And overall, mobile GPUs have limited capabilities. So maybe even they support, let's say, a lot for a target. Maybe if you use too many, then the performance will drop very quickly. The same, for instance, for uniform buffers. Maybe they can support 64 kilobytes, but if you use more than specific amount of memory, then suddenly the performance also slow down. So that's what I mean by overall limited capabilities. On the other side, we have desktop GPUs, desktop PCs, home consoles. So they are very powerful. Arithmetic operations are very fast. You can write very complex shaders. They have dynamic branching, also very fast. They have fast memory access. And they have complete shaders, which are also very efficient. And some platforms have async compute pipes, which means that you can actually run compute shader job at the same time as you're doing graphics shader job. And so that actually it uses the hardware, the GPUs, in a more efficient way. So overall, those desktop GPUs are very capable. So our main takeaway when we implemented the default renderer in URP is to prefer fragment shaders to compute shaders. So compute shaders are as fast as fragment shaders, but only on desktop and home consoles. So there's actually a lot of platforms where actually they might more easily run slower than fragment shaders. And it's not just because arithmetic is slower. It's not like that. It's more like if you plan too many uniform buffers, if you buy too many resources, certainly they might slow down, for instance. So there are sometimes some weird restrictions on those compute shaders. We prefer to use uniform buffers to structured buffers or SSBO because uniform buffers are better cached even on very modern GPUs. So even on an NVIDIA GeForce GTX 1050, for instance, some data structure, in my case I'm taking the example of the light data for the default renderer. When stored in uniform buffers, it actually yields 33% improvement in shading time. So it's quite significant. The problem obviously using uniform buffers is they're limited in size. 64 kilobytes is the maximum size normally. And so it also means we need to have extra management to split the data into several uniform buffers. And finally, we prefer to use half type in our shaders because potentially it will decrease register pressure on GPUs that support it. So that's very specific for mobile GPUs. So now we talk about the stencil-based approach. So quick overview. Actually, I'm very sure many of you already know how it works. So we just rendered the gbuffer to store all the material properties, and then all the lights are rendered as geometry, light shapes, convex geometry. So we have sphere for point light, and we have capped round cone for spotlight. The stencil buffer is used to mask the fragments inside the light shapes for rendering, and then each light shape is rendered twice, right? The first time is to set up the mask, stencil mask, and then the second time is you actually do the shading. So you will actually sample the gbuffer and do the shading on the masked pixels. So visually we can show that. We got our testing view from the top, 4 lights. So after we render the gbuffer, we render the first light, and so we lay out our stencil mask, and then we render the light again, but this time for shading. Then we do the same thing for the second light, stencil mask, and then shading. Then the third light, stencil mask, shading. Then the fourth light, stencil mask, shading. So that's a lot of draw course already, and also a lot of render state changes. So the pros, we have very simple shaders, because the shaders for those, you don't need dynamic branching. You only have one light, just shade everything. So it's most reasonable GPUs will support it, because very old technique. And nowadays, with mobile GPUs, you can take advantage of the hardware tiled architectures, which is that you render everything on tile, so you can actually cache the gbuffer inside the tile memory and then just fetch it very cheaply for the shading. So it's exposed as render pass API on Vulkan, and is exposed as image blocks on Metal, for instance. The cons of stencil-based default shading is that many draw growth and render state change still limit how many lights can be rendered. And memory bandwidth, it's memory bandwidth intensive if you're not running on a GPU with tile-based architecture, because each light has to fetch the gbuffer. So our gbuffer layout, it's very standard. So in essence, we have 4 render targets, which are color render targets. We have our depth stencil buffer, and optionally we have a fifth render target, which is the depth as color. So if you have render pass enabled, it's more efficient to also output depth as color, because you cannot sample the depth buffer without some kind of overhead. So in that case, yeah, we need this fifth render target. We do store material flags inside the alpha channel of the first render target. For instance, if your material does not want to have specular calculation, if you do not want to have shadow mask, shadow being applied on it, this has to be stored as flag. Yeah, and we also store extra flags in the stencil buffer too. So usually it's material type, things like simple lit, baked materials usually use stencil. And also the normals are encoded, can be encoded using the octahedron encoding. So it's always 34 bits. And although it's optional, because it can be more expensive. It is more expensive if you're running on mobile GPUs. So if you disable that, you have faster shading, but also you can have bending artifacts with the normals. And in the future, we probably will need to use more render targets to support light layers, to support shadow mask, and to support motion vectors. So those 4 are likely to become 5 or 6. So that's an example about the gbuffer content. We have the albedo, the material flags, specular, the normals. Here using the octahedron encoding, so it's not really like readable. Emissive baked, backlighting. The depth buffer, the stencil. Here we can see two types of materials, and the final result. The geometric shape for the light are tightly fitted. So for spotlight, you have it's a cone, and then it's capped using a rounded sphere. So if the cone has a very wide outer angle, then it will degenerate to hemisphere, and then the point light is just a sphere. So about underpass API. So mobile GPUs with tiled-based architecture can avoid the cost of reflecting GPU textures for each light shape by caching them into on-tiled memory. And that must be rendered as extra core render target for performance reason. And so we do have an implementation for it, but we are not ready to ship it. And the main reason is because during testing, we found out that on some older mobile devices with older Vulkan drivers, actually it could be buggy. So for those particular devices, then we need a fallback and actually disable underpass and use the stencil, the version of the stencil method without underpass. But so we have to push back that release to 2021. So just to release the support for underpass. Tile-based deferred shading. So again, a quick overview. When you say tile-based deferred shading, we don't mean the GPU architecture, we mean actually a software rendering technique. But conceptually, it's the same as what you can do on a tile-based architecture, in a sense that it's trying to minimize memory bandwidth when you need to fetch the GPU textures for shading. But since it's done in software, it can be improved in many ways. So most implementation now use compute shaders, and it's very popular with desktop GPUs. So the way it works, we render the gbuffers as usual, the same as for the stencil method, same layout. But then we partition the screen into a grid of tiles, and the tiles are usually 8 by 8 or 16 by 16 pixels in dimension. And then we use compute shaders to build for each tile the list of light that affect it. So each tile is extruded in 3D space as a tiled view frustum. And then we check for all the visible light in the scene if that light intersects a given tile, and if the light also intersects the geometry in the tile, then we add it to the tile light list. So here's an illustration about, so we have the camera frustum, we have on the near plane we can see the screen space tiles, and so conceptually we extrude that tile into 3D space so that it's like a very tight view frustum, and then we have to check if it intersects a light or not. So we need to check if light intersects a given tile frustum. So intersection between a light shape and tile frustums can be tricky to calculate. Actually, it's very easy to have false positive if you use the naive intersection test. And also for spotlight, it's also even harder because they have like more elaborate shape. So for instance, here we have in screen space view, we have number of tiles. We have a spotlight, for instance. And so for a given tile, how would you calculate that spotlight is intersecting that tile? And also, you also need to calculate the depth range where this spotlight shape is intersecting the tile. So actually, it can be calculated analytically. So it's very simple for point light because it's just a sphere, and it's more tricky for spotlight, but it's possible. Okay, then the third one is we need to check if a light intersects any scene geometry inside the tile. So the scene geometry itself can be inferred by just sampling the depth buffer. But inside the depth buffer is just a collection, a list of depth values. So it's simply a digital collection of depth values. So if you have a 16 by 16 pixel dimension, if you have a tile of 16 by 16 pixels, then you have 256 depth values. But you don't have the information of the triangles anymore, the geometry inside. So how do you compare that with a list of lights? So what you can do is you can compress the depth values into a bit mask. You can do the same with all the lights in your light list because you know the depth range, so you can make another bit mask. And then you can just compare the two bit mask and using a bitwise AND operation. So if it's not 0, then you know that at least one light intersects the geometry. It's approximate taste, but usually it's quite good. And it's commonly referred as 2.5D culling. So here we have another illustration. We have a tile view frustum. We have some geometry. And so we just partition the 3D space into layers. In our case, 32 layers. And then if a layer has any kind of geometry, then we set the bit to 1. If it doesn't have any geometry, we set it to 0. Then we can build that 32-bit depth mask. And we do the same for light, obviously. So our approach for ERP, so we cut the light against screen space tiles, but without that information first. And so that allows us to do the culling either on a GPU or on a CPU. And then, as a second step, we further trim the light list using the scene depth information, but just before shading. The tiles are not rendered using complete shaders, but using fragment shaders. And that's possible because we can just draw instant squad and also with the indirect draw call. And so that opens up a path where it might be possible to actually do the whole tile-based fed shading without complete shaders. It's very experimental right now. So here our same example scene with 4 lights. So on the right you can see actually all the tiles that contain light. And you can also see here that the tiles are being rendered using the graphics pipe. And so we have the triangles here. So we need 2 triangles to make 1 tile. And that's only on platforms that do not support quad rendering. And also we actually profile it, and it has no performance impact actually between using 2 triangles and 1 quad. So here we have a heat map for the tiles. So the tiles with 1 light, 2 light, 3 light, and so on. So in our particular case here, we only have up to 2 lights per tile. But in theory, we could support more lights, 52 or 64 light per tiles. And so if we try to visualize the tiles a bit closer, so the tile data structure are stored into structure buffers or SSBOs as an array of uints. And there's no benefit in storing this information in uniform buffers because the way we access the information, we only access the information once. There's no repeated access. So there's no benefits in using uniform buffers in that case. Which is not the case for the light data, so like the position, the colors, radius, and so on of the light. When you do the shading, you actually access the same data several times, and so actually in that case, there's an advantage that you use uniform buffers. And so the light list indices can be up to 32 or 64 lights. And so in this simple case, as I said, we only have up to 2 lights per tile. So in terms of workflow, a gbuffer pass generates gbuffer. We can run the light culling pass on compute or on a CPU. And so that output a light list per tile. And then we have this tile depth info pass that take the depth buffer and downsample it and generate that bit mask per tile. And then we have a compute shader again running that takes the bit mask per tile, the light list, and then trim the light again. So we have this light list that hasn't been trimmed by the geometry, the scene depth information yet, and so we just trim it out again. It's very fast. And then we can also count the actual tiles that have light inside them and then generate our indirect argument buffer and do the lighting. So that's just draw instance quad. So the pros is it's very fast on desktop GPUs, low memory bandwidth because gbuffer is fetched only once for shading. The light culling can be done as in compute pipe if you have it, and it can be further optimized because we can do material classification on the tile, so you can know for a given tile what kind of material it has, and then you can select the most efficient shaders for it. And obviously we can further extend that algorithm by implementing forward plus for forward passes. So currently for forward pass, you can only, for a given mesh, you can only support up to 8 lights. But if you have forward plus support, then you could actually just sample the light list, and then you can just shade all your lights. So you remove the limitation of the number of lights. And then you can also extend it by doing the clustered shading. So instead of having a 2D grid, you have a 3D grid. The cons is it's not fast on mobile GPUs, and also it's using compute shaders with quite advanced features, memory barriers, atomics, group shared memory, wave intrinsics, and so it might not be always bug-free on some platform. Experimentally, could we move the initial light culling pass on the CPU? Yes, it's possible because it has no dependency with the GPU. It's not entirely novel because Passwork already tried to offload some of the processing on the CPU too. So we are doing that using ng job system and the burst compiler. So we have C# code that is being burst compiled to do the light culling. And we see experimentally it's running 25 to 50% slower than the compute shader version. And that's not bad because it's C# code. And also our data layout is not optimized as structure of array, so there's actually a lot of optimization we can still do to make it run faster. But so ultimately it really depends on your CPU and your GPU characteristics, and more work is needed to really make this viable. Performance results. So quickly, our testing is 64-point light, 1-dimensional light backlighting, and so we run that on the NVIDIA GTX GeForce 1050 at 1080p resolution, and it's very fast, obviously, and the tile implementation is the fastest. So no surprises here. And you can also see that the compute shaders are extremely fast. We also run that on AMD Radeon Pro 460, so it's MacBook Pro, I think from 2017, 2018. Again, it's very fast, and the Tilebased implementation is the fastest. We also run that on the iPhone 8, which is from a phone from 2017. And in that case, the stencil implementation is the fastest. And fortunately, our URP implementation is faster than built-in deferred. So built-in deferred is also a stencil implementation. And you can also see that for the URP tile-based implementation using complete shader, the light culling is quite significant, 2.35 milliseconds. And that's also running at half 1080p resolution. And lastly, we have the Galaxy S9 using ARM GPU, and that's running slightly above 1080p resolution. And also for that mobile GPU, stencil is faster than tile. So moving forward, our stencil solution is mature and stable on all platforms, so it's going to ship very soon. We're still doing some, our QA is still doing some performance testing. And tile-based default solution needs to be tested on more platforms because it relies on advanced compute shader features. So it's still work in progress. Our experimental CPU solution is still completely in R&D phase because it still needs to be optimized. We need to implement async pipe support for the platforms where it's available, and now we can further improve it by implementing clustered shading, and then we need to implement float plus for our forward passes, so the forward only passes and transparent pass. We have some reference here if you are interested, and that's it. Thank you very much.
Next up, Arseny Kapelkin will tell us about large voxel landscapes. Arseny has worked on game technology for the past decade, having worked on rendering, physics simulations, language runtimes, multi-threading, and many other areas. He is still discovering exciting problems in game development that require low-level thinking. After helping ship many titles on PS3, including several FIFA games, he joined Roblox in 2012 and has been working on the in-house engine ever since, helping young game developers achieve their dreams. Please welcome Arseny.
Welcome to Large Voxel Landscapes on Mobile, where we're going to talk about the terrain system that we use at Roblox, how we made it scale to larger worlds, smaller devices, and implementation decisions we've made along the way. Quick aside, what is Roblox? It's an online multiplayer game creation platform. Platform is keyword here. It means that the content is created by our community, not by us. We have a lot of users and we run on a lot of different platforms and use a lot of different graphics APIs. Now, for the purpose of this talk, we're going to mostly ignore the distinction between the graphics APIs because the terrain system is largely agnostic. However, it does have to cater to different devices in terms of them having varying amounts of memory or computational power. Here's a few screenshots from the content that our community has created. This is a screenshot from the editor with the game being edited inside it. And this is an imported height map from Mars. All of these use the same voxel-based terrain. The Mars screenshot is not to scale. When we started working on the terrain system a few years ago, we set a few goals, and the first very important one was no baking. So any portion of terrain can be modified at any point in time, might be through a script, might be through a physics-based impact, for example, explosion creates craters in terrains. We wanted a single system that fully supported 3D landscapes, so caves, overhangs, and all of this without mesh inserts. We wanted reasonably large worlds, but also we wanted these worlds to run on really small devices. So our low end at the time and today is an iPad 2, OpenGL 2-class device, weak GPU, weak dual-core CPU, and around 200 megabytes of memory total available for the game. Of course, we wanted the editor to have easy-to-use tools, but also very important for us was an existence of an API to manipulate terrain from scripts that was also easy to understand the use. For example, we want to support custom procedural generators, custom tools, destruction scripts, etc. And then for us, materials are more than just textures. They have semantical meaning, and so the more we could leverage that to make it easier to create terrain that looked visually interesting by using the material information, the better it was. So dynamism pretty much cuts out meshes, and then height maps are eliminated because we need fully 3D worlds, so voxels were mostly a no-brainer. What is in a voxel though? So for us, every voxel has a material, which is an index into the palette, and occupancy, which is a 0 to 1 value. 0 means there's almost no matter inside the voxel, and 1 means there is a lot of matter inside the voxel. This is very small, compact, and easy to understand. Everything else that we do with terrain is just a function of those two, and of course the neighbors and various material-based parameters and whatnot, which makes it easier to create content, and also it makes it so that we need to store less data at runtime. Now, why occupancy? So when we started working on terrain, we evaluated a lot of different approaches, and we settled on this one. So we looked at material-only approach where maybe there's no occupancy inside each voxel, but here there's a limitation in that our voxels are pretty large. They are around 1 meter per side, and it's really hard to build good tools that give the content creator decent accuracy when working with terrain if you only have one material index per voxel. Sign distance is an obvious choice. Our occupancy representation is close to that, but it's simpler in that you don't have to worry about the voxels that are outside of terrain or deeply inside the terrain, so it's a bit easier to script. And then the other big possibility was to use Hermite data. So there's a paper, dual contouring of Hermite data, that describes an approach where inside each voxel you store intersections, or rather inside each edge you store intersections with the geometry, you store the position, you store the normal, and then you use that to reconstruct the original surface. This is great because it's very powerful and expressive, but it's really, really hard to reason about. It's hard to script. How do you write a procedural generator for this, etc.? How do you write good tools? All of these things weren't very clear to us, so we opted for a simpler approach that loses some of the expressive power. Here are some screenshots from early prototypes. So this is the Herman data prototype that we really liked because of the amount of control that it gave you, but it was hard to author content for this. And then this is a simpler implementation that we started with, where you don't have Herman data, you just have occupancy inside each voxel. And then you do an isosurface extraction. Now, before getting into that, how do we store the voxels? So we have a sparse and multi-resolution storage. Sparse means that we don't know what the world bounds are, we don't know where the context that's interesting is in, we don't even know if it's mostly a flat world or if there's a lot of depth to it. So we store it as a sparse set of fixed size chunks. Fixed size chunks are convenient for us as a unit of work, and then sparsity is important to support varying use cases. For each chunk, it's not just the voxel content that it stores for the base voxel resolution, which is like 1 meter, but it's also a full MIP pyramid in 3D. Because it's a 3D MIP pyramid, it doesn't add that much of an extra memory cost, but it's really important to have this. So one reason to have this is level of detail, which we'll cover. The other reason to have this is that it's infeasible to store the entire voxel landscape. Like the Mars level, I think, is 500 million voxels, and it's just too much memory to store on an iPad 2. So because of this, we have a streaming system that can unload and page in and page out individual levels in each chunk based on the proximity to the player and based on the available memory on the device. So it can say that the chunk that's close to the player needs all MIP levels, but the chunk that's really far away maybe only needs the very last one, or maybe 1 or 2 last MIP levels. So this is great at reducing memory consumption, obviously, but the image generation algorithms have to take some of this into account. Now, within each MIP, so you may think of a MIP as just a 3D array of voxels, and each voxel is just 2 values, so it's just 2 bytes of data. It's a bit more complex than that, because that ends up being wasteful. We have the streaming system, but then it's inefficient for the streaming system to unstream too much data. It's better that the data is more compact to begin with. So it's very common for us to see chunks where a lot of rows are not particularly interesting by themselves. They're filled with either air, so they're empty, or they're filled with some solid material, and it's the same material per row. Because of this, we use this row-based compression in memory, where if the voxel content inside a row of 32 voxels or smaller number in larger MIPS is the same, then we just store 1 byte saying this is the material in this row. Otherwise, we store a full 2 bytes per voxel. And of course, all of this has to handle modifications, arbitrary modifications from scripts or physics changes. So we have to either unpack aggressively or repack opportunistically when we need to. So now that we have the voxel data, how do we render this? Well, we can't really trace or like remarch this directly on the GPU. We could, but definitely not on OpenGL tool or an iPad 2. So we have to generate meshes, and we started looking into marching cubes, but didn't like a few aspects of the algorithm. The topology there is a bit too random, and we wanted a bit more control over the vertex placement. So instead, we ended up going with the dual method. This is inspired by the dual contouring of Fermat data paper and naive surface nets blog post. This can, in theory, run on GPU and compute shaders, but in practice, again, OpenGL2 and OpenGL3 no compute, so we have to run all of this code on the CPU. Here's in broad strokes how the algorithm works. I mentioned that there are 4 grass voxels and everything around this is air. Then we mark every grass voxel as solid with a black dot and every air voxel as empty with a white dot. Then we connect dots of different colors, or rather we connect dots together, and then for every cell that has some of the colors different between the corners, this is a 2D picture. Of course, the actual implementation is using 3D, and so there's 8 corners of a cell. But here, if it's not all black or all white, then the cell is active. Then we have to do 2 things. One is we have to place the vertex inside a cell somewhere. In this picture, we place the vertex in the middle of the cell, which happens to align with the corners of source voxels. And also we have to connect neighboring active cells together. In the 2D case, we have to connect them with lines. And then in 3D case, in our actual case, we have to connect them with quads, which is nice because this actually means that the topology of our terrain mesh output is just a lot of quads, tends to be a bit more uniform, nicer to work with in some cases. There are some extra optimizations that you can do for raycasts and such when you know that it's just quads. Now, so we place the vertex inside every cell. What kind of parameters do we set for this vertex? First, we need to pick the position, the normal, and also we said that we wanted just one material to correspond to every vertex. It's a simplification. In the earlier example, of course, that is just grass material, so it holds. But in practice, in real landscapes, there's many cases where there's conflicting material information that comes into generating the vertex, and then we just pick the dominant one. So then for the position, we start with what naive surface nets does, which is that if you look at the edges that connect black dots and white dots, you can place a point on this edge using the typical isosurface-based interpolation. For us, it's occupancy, and classically it's based on signed distances, but it's similar where you place the point. In this case, you would place a point in the middle of the edge if the occupancy was 1, to push it furthest out along the voxel direction, and then if it's 0, then you would place it really close to the corner of the voxel, to the center of the voxel. And then you can look at every cell, and every cell has a few edges that have these mismatching colors, and then you can take all of the edge points and then average all of them together. So this is what naive surface net does, and this is what we started with. And then to compute the normals, we just average triangle. So this is very easy, very simple, gives you similar results to isosurface extraction from signed distance fields. Now, there is a lot of leeway in where you place the vertex though, and we aren't using that. So on this screenshot, for example, you can see that at the top, the terrain looks very blocked, and this is because this was what happens when you place the vertex in the midpoint in the center of every cell. And at the bottom, this is the averaged approach that we use from naive surface nets. Now, you can actually do a lot of things though with the vertex position. So in this screenshot, we are actually interpolating this decision or like the vertex position between these 2 choices based on whether the vertex is above ground or below ground. But of course, average and just placing the point in the center of the cell is only 2 options. So here's one more. Here's what happens when you take a random offset pseudo-random based on the cell identity, and then apply it to the position and then constrain the resulting position to the cell boundaries, which is not necessarily crucial, but it helps to avoid self-intersections. And this also gives you a nice kind of different look to the terrain, nice different shape. And so inspired by these possibilities, we ended up doing exactly this, where we pick a material for a vertex, and then based on this material, we define a procedural deformation function that places the vertex somewhere within the cell. Maybe it's the center, maybe it's the average, maybe it's one of these shifted by a random offset, maybe we quantize it to some multiple, etc. There's a lot of different possibilities here. Here's just a few of those. This is great because this is where we start saying it's not just the occupancy that matters, really the material choice defines the shape of the terrain, and so it makes it easier to build interesting looking terrain without too much effort. Also, we use the material information to define normal blending, so you can compute normals just based on the averages of the triangle normals, but then you usually have to have some sort of crease angle cutoff. In this case, though, we can say this material always has soft edges, or this material always has hard edges, and therefore needs to separate the triangle normals when averaging. This is an example of this in action. There's a few different materials here. There are some that use just smooth average position. The bricks use the midpoint, and then rocks use random offset. The pavement uses quantized offset, so it has a bit more kind of man-made looking structure, but still not all that uniform. And then it's hard to see here, but the other material uses barrel, which is smooth on X and Y, X and Z, and then it's always the center along the y-axis, which means that when you build plateaus, the top is always pretty flat, which is nice. So there's a lot of different possibilities here that you can imagine. Now, okay, we have the vertex position now, and for every vertex we have the material index, but what do we do with this then? So here's the triangle, it has 3 vertices, each vertex has material. How do you compute the color? Well, so you have to sample textures from 3 materials and then interpolate based on barycentric somehow. But then what kind of projection do you use? What kind of texture mapping do you use? Because all of this has to be dynamic based on where kind of the points are. Well, the classical way to do terrain texturing that avoids distortion is triplanar mapping, where you have 3 projection planes, x, y, yz, and xz, and then you blend between all 3 of those using the normal. So then you have 3 samples from different materials, and then for each one you do 3 triplanar samples. And then, of course, this is not just albedo texture, there's also normal and roughness, and so you have 27 fetches. And even if you don't have albedo, even if you don't have normal and roughness, you still have 9 fetches, which is a lot for an iPad 2. So we do not do that. Instead, what we do is we use an approach inspired by quilting, by the paper Real-Time Image Quilting from SIGGRAPH 2011. The basic idea there is that you take each vertex and then you look at the incident triangles, and then you project a patch of textures onto that, and then in the vertex, in the center vertex, the influence of this patch is maximum, is 1, and then towards the edges the influence goes to 0. And then you overlay many different patches like this, and in combination these end up defining your visions. So for each vertex we're gonna do only 1 texture sample. This means that for a triangle, we do 3 in total if you only care about albedo, and if we do 9 if we also care about normal and rough. Now, how do we make this project? Well, we need to pick a projection plane, or the most obvious way to do this is to pick a projection plane. And we pick 1 per vertex to minimize the distortion. This doesn't result in triplanar mapping, but it can result in something reasonably close to triplanar mapping if you're careful in your plane selection. We could store a full plane equation, but instead what we do is we store a plane index, and we just have 18 fixed planes. 18 is just the smallest number that worked reasonably well. Here's how this sort of looks like. Here's a single patch where there's a vertex in the center, and then there's a single projection plane, and then all triangles around this vertex end up sampling this texture with this texture projection, and then the blend weight depends on barycentric coordinates. And then if you look at the entire terrain with that patch taken out, you can see that there's a lot of space here that's just covered by these different patches, and you can imagine that if you added the previous slide to this slide, you will basically get the full resulting terrain. Now, one other thing that we'd really like to do, though, is to fix the tiling artifacts that happen far in the distance. And if you think about this, well, we already take a vertex and then we do some texture splat using a projection plane that we pick per vertex. Well, we also can augment this transform with a random shift and random rotate, and the randomness could be based on the vertex seed so that it's all stable. This helps a lot in breaking up the variation. And also this randomness could be dependent on the material. For example, if you have a brick, you really don't want to rotate the samples of the brick, but you can shift them just fine, especially if you shift by sort of brick-sized granularities in UV space. Now, if you imagine a triangle where the three materials in the corners are the same, effectively you end up having three different randomly rotated and translated layers all blended into each other, which breaks up the tiling very nicely. Here's how it looks. So here's the scene without the tiling, without detailing, where you can see a lot of tiling artifacts on grass, which you could try to hide with texture art, but it's really hard to do a good job there. And even on water, where we have several different layers of normal maps blended together, you can start seeing tiling artifacts if you look sort of close. And this is at this angle at less, at more oblique angles, you see tiling on even on water if you don't do anything to fix it. This is what happens when you apply the detailing. You can see on the water, there's basically nothing that you can notice, no tiling issues whatsoever. On grass, you can sort of see the lines somewhere where the texture rotations happen to align in such a way that some prominent feature of the texture is still visible, but it's largely speaking really, really good. And this is all completely automatic. Now, what we end up with is that for each pixel of each triangle, we do 3 texture samples, or we do 9 texture samples if you need full PBR texture set, but 3 material samples. And depending on the configuration of the triangle, they end up serving different roles. So if the materials are different, then we need to do this because we need to blend between the materials. If the materials are the same, we still need to do this because we need to do triplanar. And if the triangle is flat along the ground, so that you don't even need triplanar, these samples are still they do still end up being useful to break up tiling. If we are really desperate, which we are on some of the low-end devices with very weak GPUs, we can go one step further and say, well, we have 3 texture samples that we need to do, but really let's just do one with the highest weight. Of course, this is not great from the quality perspective. You see very hard seams between materials, etc. But if it's more important, if performance is more important than quality on some of these devices, then it's still a viable path that you can take, and we do take. Now, in terms of scaling up, so the biggest problem with this technique tends to be that the linear blend isn't great for a couple of reasons. If you have 2 different materials, blending between them just fades one texture into another, which is just not great because this is not really how the real world looks, how the real world works, doesn't look natural. If the materials are all the same, then the big issue is the contrast gets lost, and there's sort of, again, odd blends between different parts of the same texture you sometimes can see. We've experimented with 2 different approaches to fix this. One is height-based blending, where you have a height map that you can store in the roughness texture if there's an extra channel there, which there usually is. And based on the height of different materials, there is some region where you still do the blend, and there was some region where the blend is maybe more aggressive and one of the material wins early on. One alternative implementation is histogram preserving blending, which is the work by Eric Heitz. So the height-based blending mostly fixes blends between materials, but it also can help fix the contrast problems as well. Histogram preserving blending is mostly good for fixing contrast loss. Here's an example of how this looks like in action. So this is the vanilla blend, nothing special here. And then this is the height-based blend. And so if I go back and forth, there's 2 things that you can see. One is the transition between 2 materials is much more natural. The grass still sort of, it grows through the bricks, but in a more organic fashion, even though there's still some region where there's a blend. And the other one that you see is that the second screenshot has higher contrast, and this actually matches the real art, like the texture that we started from, better. So we've talked about the textures. Now, one downside with this amazingly beautiful scheme about 3 textures, texture samples per triangle set, etc., is that hardware doesn't really want to work this way. So the fragment shaders usually don't expose barycentrics directly, they don't expose the vertex shader outputs. And to make all of this work, we actually have to pack a decent amount of information into each vertex. We have to pack effectively some information about the vertices in the same triangle, other vertices in the same triangle into the vertex, and then duplicate that. This is not great for memory. This is not great for performance. We kind of have to do this. We experimented with alternative implementations here, so for example, using geometry shaders on desktop hardware. It worked pretty well, substantial memory savings, comparable performance, maybe slightly better. But of course, geometry shaders aren't available on many mobile platforms, and then aren't advised on others. Hopefully, at some point in the future, it's either going to be that we can use mesh shaders if they ever happen on mobile, or one alternative implementation is to use direct access to barrier-centrics, which you do get on consoles. So in theory, some GPUs may be able to provide this. But short of either of that, there are some kind of hacks that you have to do, and we compensate for this by aggressively bitpacking data, bytepacking. So then, Drokel-wise, again, OpenGL 2, iPad 2, weak CPU, pretty thick driver layer. We have to minimize that. To minimize that, we have to make the decision where every chunk is drawn in a single Drokel, and to do that, we have to pack all of the material layers used in the level into either an atlas or a texture array. We prefer texture arrays, of course, but OpenGL 2, OpenGL 3, OpenGL 2 mostly, so we have to use an atlas, and inside an atlas there, we have to leave large borders to have MIPS operate in terms of filtering. But when we can, we do use texture arrays. So this is great, both because it doesn't really matter as much what materials you use in your level, it roughly performs the same way, and also because all of the material information is kind of front-loaded and set aside in these atlases and texture arrays and constant buffers. So really for every chunk, you just have to update a uniform that corresponds to where this chunk is in space to make bitpacking possible, and that's it. So even if you do have to render many chunks, like hundreds of chunks per frame, even on OpenGL 2 plus devices, it's still pretty fast on the CPU. Now, at some point, though, you have to start introducing level of detail for a variety of reasons. So CPU cost becomes prohibitively expensive if you have too many draw calls. Of course, the GPU cost in terms of triangle count, and also because of the streaming system, you don't even have all of the voxel data always resident in memory, so sometimes we have to use voxel data that's not the top MIP. To organize all of this, we use an octree, and then we only render leaves of the octree, and then these leaves can be split when the leaf is close up, and then they can be merged if they're far away, which gives you these level of detail transitions. For us, every leaf that we do draw, we always match it as if it's 16 cube voxels, which is just a trade-off between the draw call size and the update cost. Whenever voxel changes in a chunk, we do have to update the entire chunk. Our meshing is not incremental, so there's a trade-off there, with 16 to 32 cubes probably being reasonable trade-offs. And the nice thing is that we do use the voxel data for this, so we don't have to go through the top highest resolution voxel data, create a high resolution mesh, then simplify that, etc. We can just take the downsampled representation of voxels that we already have in memory from the MIP pyramid and work with that. Now, the biggest problem, of course, is what do you do with the gaps between levels of detail? If the level of detail in the neighboring octree nodes is the same, then it's all very simple. Our meshing algorithm handles all of this beautifully. It has edge consistency, edge rules, and all of this. Now, if they're different, then of course there's going to be a gap between these two. Now, ideally, and this is what the dual contouring paper does do, you would generate triangles to stitch this gap precisely, matching vertices to vertices, etc. We do not do this. We do not do this for two reasons. One is it's really complicated to write this code, to get this code to be correct, and to get this code to be efficient. It's just very hard because it's a very complex topological problem, and there's cases you have to enumerate, and there's lots of branches that you have to take, and all of that. So it doesn't end up being very efficient, and it doesn't end up being very simple. But also this complicates the management of the LOD data substantially, because whenever an LOD switch happens, you now have to remesh the stitch between this chunk and some neighboring chunks. And you have to do all of this in time, because when you do a transition from one level of detail to the other, it would be nice to do the transition simultaneously for everything that is a result of this operation, and all of this gets very painful to implement. So instead of doing that, we use the next best thing, which is skirts. So this is a classical technique from the height map rendering world where you generate extra overhang geometry for individual cells and then hope that that will cover the gaps. So for us, that just means one extra triangle. And we do this based on just one extra layer of voxels. We do some voodoo magic to kind of patch up the voxels so that the geometry ends up being more reasonable. But fundamentally, the geometry in skirts is not very reasonable for us, but it doesn't matter as much because we use depth bias to kind of hide it. We push it inside the screen so that if there's any non-skirt pixel, we draw that instead. This means that you only see the skirt geometry inside the gaps, and these gaps tend to be reasonably narrow to begin with, so it doesn't end up being a big problem. Also, this is using the exact same meshing code with all the performance optimizations, etc. So it's actually reasonably fast and it's cheap enough to generate for every chunk. It does come at maybe 10% extra memory cost, but the level of detail by itself more than makes up for it. Now, here's how this looks like in practice. And this is where the simplicity of this approach really comes in. So you see the LOD0 chunks and LOD1 chunks, and you see the the blue stitches between the 0 and 1. This is the skirt geometry. For every chunk, you need up to 3 of them, because for every chunk, we generate stitches from the finer level of detail, LOD0, to the coarser level of detail, LOD1. This means that for every chunk, there's 3 sides that point where the neighbors are within the same octree cell, and by the octree construction, these cells must be the same level or finer, so you don't need stitches there. So there's at most 3 sides that you need stitches on. And in a 2D picture, so there's the base, which is like the center of the chunk, and then there's stitch X and stitch C, and you only have to render them if either of your neighbors on either side needs stitching. So has a different level of detail, or rather a coarser level of detail than you are. Now, the beauty of this is that, okay, so there's at most 3 sides, and one of them, the Y side, the up, Y being up, is almost never used for us just because of how the level of detail is computed, etc. And if you order your index buffers for the stitch geometry and the base geometry in one consecutive kind of index range, stitch X, base, and stitch Z, then you can, if you only need X or Z or both or neither, it's still one single draw call to just adjust the index range. And so it's almost always still the case that we only need one draw call per chunk. We only need 2 if for some reason we need to draw the Y stitch. Of course, for this to work, you have to do this depth bias conditionally within the same draw call, but this is actually fine because for us it's just that the vertex shader pushes this geometry into the screen and can do this based on one bit that is stored somewhere inside the vertex that says, is this a stitch vertex or not? So this covers most of the basic terrain, etc. Let's talk about a couple of examples of where we take the material information that we have and do something material specific, very material specific with that. So one example is water. Water in general doesn't fit very well with this framework of meshing. If you just say, well, we mesh the interfaces between solid and air, well, water is not solid. So to make water work, we really have to mesh the interfaces between solid air, solid water, and water air. Solid water is important for underwater rendering, and then water air is important for actually drawing the outer surface of the water. And all of this can actually be done during the same single meshing pass, which is really nice because it doesn't actually cost more performance, much more performance, I should say, to extract water geometry as well as solid. Instead of 2 colors solid air, we just use 3 colors solid water air. And whenever there is a difference between the colors on the interface between 2 voxels, this is where we know that we need to place quads. Now, we do need to render the water separately. I mean, it's translucent, it has separate shading, etc., etc., etc. So this is where we actually do use 2 draw calls per chunk if a chunk has water and non-water materials. And there's some care that has to be taken due to some specifics of how we mesh all of this. So if you were to apply this naively, something you would see is water bulging. Not sure if this is very obvious here, but there's a ground that goes kind of down, and then there's a connection with water, and then the water grows back up. And this is just because of how the averaging in the naive surface nets work with the positions of the edge points. But you can fix this by doing a water-specific deformer because we know the material and push the water down, and it ends up looking nicer and more like a lake. We play some other small tricks here with geometry generation, although there's still some space to improve this, because these connections sometimes end up looking a bit finicky. For water rendering, there's nothing very unusual here, I would say. This is where we do start seeing some desktop-only features. So in general, we use tiled animated normal maps that we have pre-baked ones, just based on a wave simulation. We have a lot of vertices in general in terrain. It's reasonably uniformly spaced vertices, so we might as well use them by displacing them to do geometric waves. And then there's some extra underwater and refraction simulation. So on desktop, where we do have the depth, we can also do screen space refraction and screen space reflection with an ATEP trace. One big aspect, two big aspects maybe in water rendering that we will improve on in the future is flow in general and shorelines in particular, where we actually do have some information about which vertices are on the border and which aren't. And in this case, you can see a bit of a darkening that we apply in the border. So we can place foam automatically and things like that. We haven't done that yet. This is how the underwater shot looks like. This is why it's really important to mesh the solid water interface, otherwise you just won't see this. And this is, here you can see the underwater fog and sort of reflection, refraction accidentally sort of working in the underwater simulation. And of course, this being voxels, there's no real restrictions of what you do with water and where you can place them. So this is an example of just there's a water bubble that doesn't fall down because we don't have fluid simulation quite yet, but you can see refraction and other effects here as well. So past water, there's also a question of general geometric fidelity and kind of terrain looking interesting beyond the textures. And there's a lot here that we can do in theory just based on the materials and tessellating things more and creating formations that are visually interesting based on the material. But one very obvious thing to do, which is what we did do already, is to do clutter or foliage, or in general, we want a lot of small objects automatically placed on terrain based on the voxel types of the material. We experimented with card-based grass, and it can look really nice if you have a decent texture and you have to be careful of how to organize the mesh, etc. But then when you run any card-based grass, despite it doesn't matter if you use blends, it does matter, but it doesn't matter as much if you use blends or discards, it still ends up being substantially slower than geometric grass on tilers, specifically on deferred tiling architectures where the hidden surface rejection pass can remove a lot of the geometry that's not visible. If you do card-based grass, you mostly just don't use that, and so that's not great for performance. So we like the look of card-based grass a bit more, but we ended up going with geometric grass just because it's much more performance friendly and we can actually ship this on mob. Here's how grass looks like. So this is a dense field where you can see some animation and some shading experiments. And here's a much less dense field with a bit of a different kind of structure and running with the rest of the environment as well. So grass ends up being a bit of science and then a whole lot of kind of art and a whole lot of work to make it look just right without paying too high of a performance cost for it. We do end up rendering individual blades, but of course we compact all of these blades into larger index buffers, vertex buffers and index buffers. And then each blade is just 3 to 5 vertices per grass blade. 3 is like the simplest one, and 5 is the simplest grass blade that you can still bend, which is really nice up close. Important point is that when we place the grass, so we place it based on the triangle surface that's generated by the mesher, but you have to be really careful and use stable randomness. So we see the random number generated using the seeds that come with the vertices. The reason being, if you imagine a chunk, and so whenever anything changes inside the chunk, you have to regenerate the entire chunk. And then if there's a crater in a chunk that wasn't there before, you really don't want that to affect other parts of the chunk where grass used to grow and it should still grow, and it should grow in the same places. And then shading is just a whole lot of tricks, a whole lot of tuning. There's wrap diffuse that we do. We do translucency simulation sort of, but it's an approximation that's pretty cheap with a few LU instructions. And then a lot of the interesting visual variety in grass tends to happen because of the clumping of grass, and you have occlusion. And of course, all of this is very, very hard to actually simulate on a mobile device. So we do a lot of height-based approximations for this with gradients for diffuse and specular and normals that are slightly different from the geometric normals, etc., etc. I don't have a lot of time to go into more details, but here's a beautiful picture of our rendering engineer who worked on all of this, studying the light interaction with the grass blade. So we're pretty happy with where we are with terrain in general, but of course, there's a lot of work still to be done. A lot of this was focusing on kind of what is practical on old mobile devices, on ES2 class devices, maybe ES3 with not a lot of power, but of course, the technology has moved since then. And also there's a lot further that we can push this on higher end desktops, right? So high fidelity geometry is something we want to explore, where we can actually tessellate the terrain geometry more in various ways. Shading is something where it's very easy to make a lot of kind of progress in various places. I already mentioned some improvements on water. Texture mapping is interesting because in general, we're very happy with the texture mapping scheme that we kind of landed up on. But it does right now, due to how it's implemented, does mean that in some cases you do see stretching on some triangles, and it could have been mapped a bit better. And of course, one big general theme in Roblox is that as we develop the platform further, our users and we want larger and larger worlds. And so right now, the practical limitations of the system are perhaps around 1 billion voxels with the streaming system, paging things in and out, etc. Like, this is reasonably practical to achieve today. And so if you imagine a 10 square kilometer world, this is fine. But if you imagine a 100 square kilometer world, then for each 1 by 1 meter, you get like 10 voxels. And 10 voxels is not enough, because that's just 10 meters of depth information, and you really want 100 or more. And so figuring out better compression schemes and, in general, smarter ways to do level of detail where maybe we lose less fidelity of geometry for similar performance and memory gains would be interesting to explore. So that's all I have. Thank you for listening to the presentation.
Next up, Romain Guy will tell us about Filament, a high-quality, high-performance renderer for Android, as well as other platforms. Romain leads the Android Toolkit team at Google, responsible for the UI Toolkit and a suite of libraries called Jetpack. One of the projects of his team is Filament, a real-time cross-platform physically based renderer mainly targeted for mobile devices. Previously, Romain worked on various parts of the Android graphics stack, including designing and writing the hardware-accelerated 2D rendering pipeline for the UI and color management. Please welcome Romain.
Hi, my name is Romain Guy, and welcome to this talk about Filament. So, before we get started, what is Filament? It is a physically based real-time renderer for Android, iOS, macOS, Linux, and Windows. It supports OpenGL ES3, GL 4.1 for desktop, Vulkan on mobile and desktop, Metal on macOS and iOS. It is just a rendering engine, it is not a game engine, and it's currently used by AR applications at Google, for instance. Filament is developed entirely in the open. You can find it on GitHub at /Google/Filament. The design goals behind Filament is that we want it to be embeddable. It has to be a small engine. It's about less than 500 kilobytes for ARM64, for instance, with Vulkan and OpenGL support. And ARM64 is actually our main target, obviously, for mobile devices. We also want to target high rendering quality, including advanced material models like cloth rendering, clear coat, anisotropy, and advanced effects like screen space refraction. We also try to stay physically based as much as possible, including for our camera setup or for light units. If you are familiar with Filament, it may be because of its documentation. It's a long document explaining all the theory and the math and the choices behind our PBR implementation. And this documentation was born from the fact that we strive to understand everything that we do. Every time we make an approximation, every time we decide to choose something that's lower quality or higher quality than an alternative, we like to understand why we make that decision. It is always a conscious decision. So you may disagree with the results, but at least we have an explanation as to why we made the decision. And if you haven't seen that document, I highly recommend you take a look at it. It's a little bit out of date. There are some things that we've done since then that are not explained in the document. Hopefully we'll change that soon. All right, we're going to talk about performance improvements that you can make in your engine, but there are two major optimizations that you must implement before anything else, at least for mobile. So the first one is handling tiling GPUs properly. So on mobile, bandwidth is at a premium. It has not been improving quickly, to say the least. And to help with bandwidth management, tiling GPUs or tilers, on those devices, you need to manage resolves and unresolves properly. So resolve or store is writing the GPU tile to memory. And unresolved or load is the opposite, of course, loading the tile from memory. It is explicit on Metal and Vulkan, and OpenGLES drivers try to do this using heuristics. For instance, if you do a full screen GL clear, the driver will most likely skip the unresolved or the load. So you can control those explicitly with OpenGLES using GL invalidate frame buffer, which is part of GLES 3. There's also an extension for GLES 2. When you call that function before any draw call, you are preventing unresolved, you prevent the loads. When you call it after the draw call, you can prevent the stores. It is, however, tricky to use this API manually. You must know whether you need the content before or after the current pass, which may be fine when your rendering engine is simple, but as soon as you start adding more and more render passes, especially when they can be enabled or disabled at runtime, things get really complicated. So in our implementation, we rely on a frame graph to do this for us. So what our frame graph does is track all the dependencies for all the buffers that we use. It also manages the lifetime of those buffers, and it computes the discard flags for the buffers. So the discard flags are the flags that we pass to GL invalidate frame buffer, or to the equivalent in Vulkan and Metal. And we compute those flags based on the current buffer and the current pass. So if a buffer is never read after the current pass, we can discard it at the end of the pass. If the buffer is never written to before the current pass, we can discard it at the beginning of the pass. We can avoid the load or the unresolved. And if a buffer is cleared by the pass, we can discard it no matter what happened before. So here's an example of our frame graph. So every orange box is a render pass. So here we have a color pass, a post-process pass, so that's color grading, tone mapping, dithering, and a pass of FXA, and finally there's the output. It's fairly simple, and managing loads and stores here would be pretty simple to do by hand. Now, if we turn on a few more features, we end up with this frame graph. So here we have directional shadows, spot shadows, screen space shadows, screen space refraction, screen space ambient occlusion, bloom, color grading, FXA, MSA, and we have more features that are not even enabled, like depth of field. So writing code that manages the resolves and unresolves properly in these kind of situations quickly becomes extremely difficult, especially as the dependencies between the passes and the buffers that can change at runtime, like I said. So let's take a look at a concrete example. So this is the anatomy of a frame on a Pixel 4 where we don't use GL invalidate frame buffer. So first, we have our shadow passes. We're going to ignore those for this example. Then we have the color pass, and that's the one that interests us. So in this color pass, our HDR buffer is in RGBA 16F, so we have 64 bits per pixel. It's at 1080p. We have MSA turned on. And we're going to zoom in on that pass, but if you look at this pattern of colors, all those little blocks, like the red and green blocks, you can kind of guess that each one of those repetition of the pattern is a tile. Finally, after that, we have the post-processing or color grading pass, and then finally we have FXA. So if we zoom in on the color pass, every instance of the pattern looks like this. First, we have the rendering itself, so that's going to stay there. Then we resolve the depth. We write out the depth buffer, which is unfortunate, since after that, the color grading or the post-processing does not need that data, so we use bandwidth for no reason. Then we resolve the color itself, so that's good because we need it for post-processing. And then there's an unresolved. So that's actually loading, reloading the tile for the next tile effectively. But we always render the whole screen. I mean, that's the common thing to do in 3D applications. So we're doing that whole load, which clearly costs a lot of bandwidth for absolutely no reason. So that's a little silly. Now let's look at the same frame after we added support for GL invalidate frame buffer. So the render passes are the same, but if you look at the color pass, the pattern is a little different. And if we zoom in on it, we can see we still have the rendering, and now we only have one resolve. We resolve the color. So we don't resolve the depth anymore, and more importantly, we don't reload the tile. So on a Pixel 4 at 1080p, all those extra resolves and unresolves that we just got rid of can add up to about a millisecond per frame. It depends on the frequency of the GPU at the time, but it is not negligible, and it's an easy optimization to implement. Now we can do better than this. So recall that our color buffer in this example is RGBS16F, which means that each color resolve has to write 64 bits per fragment. Makes sense, right? We need this data for post-processing, but do we really need to write it out to main memory? So turns out that most of the time, or at least very often, we only need the current fragment for post-processing. If we don't do bloom, if we don't do screen space refraction, if all we do, for instance, is FXA, color grading, tone mapping, we only need the current fragment. And that's a perfect candidate for Vulkan subpasses or the shader frame buffer fetch extension in GL that lets us read the current content of the tile from the shader. So here's how we use it. It's really simple. First, we start with 2 render targets, and they are both bound at the same time. And that's key to staying in the tile. Note that in the render pass, in the color pass, we render into the HDR target, but we never load or write to the RGBA target. That's for post-processing later, but it's there. So then we render a full screen triangle to do our post-processing, and that's going to write out to the LDR target. It's going to first fetch from the HDR target, where we just rendered our color pass. Then it's going to do its work, applying color grading, tone mapping, and so on. And finally, it's going to output to the LDR target. And the outcome of that is when we look at the anatomy of the frame, if you look at the end, the color grading pass is gone. It has been merged with the color pass because the driver can see that we can do both at the same time within the tile, so they've been collapsed together. Interestingly, if you look at the patterns, we can still see the resolves between the render blocks, but those resolve in RGB8 instead of RGBS16F. So it's a lot less data. It's half the data, so it's a lot faster. All right, the second major optimization that you can implement is to use half floats or 16-bit float or FP16 everywhere you can in your fragment shaders. By doing so, you can run twice as many instructions per cycle on mobile GPUs, which means that you will either get better performance, or you will use less power, or you will generate less heat. Any one of those is a good thing on mobile devices. And it's also really easy to do with GLSL. You can just change your default precision to medium P at the top of your shader, and that's pretty much it. You're done. Or are you? Well, almost. There are 3 problems that you need to deal with. The first one is that the minimum value that you can represent is actually not that small. That value here can be easy to reach when you start squaring. Very often our parameters for materials are between 0 and 1, or your dot products are between 0 and 1. And when you square them or raise them to higher powers, we're going to get very close to that value. And because mobile GPUs don't support the normals, we're going to flush to 0, which can lead to all kinds of trouble when you divide by those values. The second issue is that the max value is only 65K or so, which is not that big, and we're going to see an example of why it's not enough. And finally, once we reach 1024, we lose all fractional precision. This makes half float unsuited to store things like texture sizes, UV coordinates, world positions, vertex positions. For instance, if you use meter as your unit in your engine and you store positions in half floats, at 1 kilometer away from the origin, you would have a precision of 1 meter, which is pretty terrible. All right, so let's look at some of the solutions you can use. First, you can clamp values so that you don't end up flushing to 0. For instance, this is how we clamp our roughness value. And that number 0.089 is not random. Here's how we came up with it. We looked at our BRDFs. Somewhere in the BRDF, we divide by the roughness raised to the power of 4. We know that the minimum value in FP16 is 2 to the power of minus 14, which means that we need the roughness to the power of 4 to be greater than 2 to the power of minus 14. And with a bit of very simple math, we can figure out that the value has to be 0.089 to work. Of course, sometimes you don't have a choice, either because the math is too complex or there are too many terms that come into play. So this is an example of the anisotropic normal distribution function in filament. If you look at the variable d and d2, you can see they use the high P keyword, which means do the math in FP32. So why is that? So first, we take two roughness parameters. Both of those are the roughness along the tangent and the bitangent, and they're effectively the roughness squared. And then we multiply them together, so we have roughness to the power of 4. Then we have a dot product that uses this variable a2, so we end up with roughness raised to the power of 8. And that won't fit in FP16 unless we climb the roughness to a value of 0.29, which is way too high. That means the minimum roughness we could have in our material is 0.3 almost. So that's not good. So our solution is to just give up and do a bit of math as little as we can in FP32. Here's another interesting example. Sometimes computations can tend to infinity, as is the case with the visibility term that we use. Unfortunately, that can lead to tons of issues on mobile. You're going to end up with black pixels if you output, not a number or infinity. So to avoid this, in those situations, we just clamp to float max, and that solves the problem. And here's the one last problem. So this is a simplified version of lighting. We multiply intensity of the light by the exposure by the BRDF. But things get a little more complicated when you look at potential values of those different variables. Because we use physical light units, our sun can have an intensity of 110,000 for a bright day. And the corresponding exposure is a very small value. So first of all, the sun, because it's 110,000, that's greater than the maximum value we can store in a half float. And the exposure for a bright day is smaller than what we can store in a half float without flushing to 0. So the solution here is to pre-expose the light intensity on the CPU. And when we do this, we end up with a value that's much more reasonable. It's about 2.8 in that example, and that's what we pass to the shader so we can keep our computations in half floats. All right, so using those techniques, we were able to do all of our lighting in FP16. It can be tricky to chase these kind of artifacts caused by computations in FP16. It took us a while to find one in our code, FXAA code. So sometimes you have to fall back to FP32, especially when you deal, like I said, with UV coordinates or texture sizes or vertex positions. But it is worth it. And with even desktop GPUs now gaining support for FP16 computations, it can be worth it there as well. All right, now let's take a look at how we can make a couple of our BRDFs faster. And by faster, I mean making them more wrong. So here's the height correlated Smith normal distribution function described by Eric Heitz in Understanding the Masking Shadowing Function in Macrofacet-Based BRDFs. And it's the term that we use in Filament, at least on desktop. If you look at it, it has two square roots. But let's focus on the square roots. If you look under the square roots, all the terms, more or less, are squares. So if we take a closer look at that and we squint really hard, we have what? A square root of squares? Wouldn't that be the same as having no squares and no square roots? Obviously, this is horrible math. That's what I call graphics math. But we are here to make things look good and run fast. So let's give it a try. And so when we do this, we can simplify the visibility term quite a bit, and actually it simplifies all the way down at the bottom to a lerp function. So the implementation becomes this. We have a division, a lerp, and a couple multiplications. So it's very cheap. And this absolute horror of mathematics was described independently by Earl Hammond at GDC 2017 in PBR diffuse lighting for GGX plus Smith microsurfaces. It always makes me feel a lot better when I see someone else do something horrible. And I believe that the Hammond shipped that in Titanfall 2. All right, next up, clearcoat. Clearcoat is implemented as a second specular lobe on top of the base layer. So it's great to create beautiful materials like lacquered wood on the left here or coated carbon fiber. And it's fairly easy to implement. But it is a second BRDF that we have to compute for every light. So for clearcoat, we decided to replace the distribution function that we had the visibility function by another one described by Kellerman in the paper, a macrofacet-based coupled specular matte BRDF. Eric Heitz, him again, has shown in his own paper that this term is not physically based, but it is incredibly cheap and it still looks great, so we adopted it. Especially when you layer the clear coat on top of the base layer, it becomes more difficult to see the difference between this visibility term and other terms. So since we have this other approximation that we just saw earlier for the visibility term, we might revisit that decision. But this is so cheap that, might as well keep it. And also, it's a kind of things we decide to do. It's a trade-off, right? When we do this kind of simplification in Filament, it allows us to add another feature that might increase the quality somewhere else in a more visible manner, so it can be worth it. But I want to mention tone mapping really briefly. Some of you are probably going to scream when you're going to see me conflate tone mapping, gamut mapping, and transfer functions, but bear with me. So Krzysztof Narkowicz, I hope I'm not butchering his name, a few years ago popularized a fit of the ACES RRT plus ODT for sRGB output. It looks like this. And it was popular because it is very simple, very easy to implement. You apply it in linear space, and you have to apply your transfer function or your gamut mapping if you want to do something fancier. Especially, it's very simple, especially compared to the real ACES process. And here's what we propose instead for mobile. It's a division and a MAD, extremely fast, and it also happens to bake in an approximation, a gross approximation of the sRGB transfer function. It's all kinds of wrong, but it's good enough for mobile. And like I said, it is cheap. So if we compare it with the ACES fit, both after applying the transfer functions, it looks like this. On the x-axis, we have a logarithmic scale to make it easier to do the comparison, but we can see we're pretty close. And if we compare screenshots, so this is the ACES fit, and this is our approximation. And if I toggle back and forth, you can see the approximation is a little less contrasty, a little less saturated, but still looks great. And mobile devices, you don't control the viewing environment. So it could be in a completely pitch black room, or it could be outside under a bright sun. So honestly, it's not going to matter that much. It just has to be good enough. And like I said, it's going to be fast. Now, in the latest version of Filament, we don't use this anymore. We switched to a lookup table, so we can do color grading and tone mapping and transfer functions for free. We also let you choose your tone mapper. It used to be baked in. So we've abandoned it. But if you need to target underpowered GPUs, that might be, or something like this might work for you. Onto image-based lighting. So we started, unsurprisingly, with spherical harmonics for the diffuse component of indirect lighting. We use 2 bands or 3 bands, depending on the situation. And spherical harmonics are great because they're easy to compute offline. They're really cheap to apply, especially when you only use 2 bands on mobile, for instance. And they can yield very good results for low and medium dynamic range environments. So here's an example. It's a scene with a rough dielectric grass sphere lit by a 2-band spherical harmonic. The environment is medium dynamic range. It's about 9 stops, 9 EVs. So it looks great. It's fast. Love it. Now, unfortunately, spherical harmonics don't fare so well in high dynamic range environments. So in this example, we have a dynamic range of 21 EVs. The center of the sun is about 300,000 in this picture. So this is not something you would see in a game. At the very least, you would remove the sun to use an analytical light instead. But some of our users have asked for this feature, and it looked terrible. So here with 2 bands, we can see there's ringing, and the back side of the sphere is completely wrong. It's too dark, but at the same time, we have this wrapped lighting. The light goes around the object. That's all kinds of wrong. We can do better. So if we switch to 3-band spherical harmonics and we apply a low-pass filter, we do a kind of windowing, you can see the result right here. It looks a lot better compared to 2-band, so 2-band, 3-band. But it's still extremely wrong. We still have this wrapped diffuse lighting, and this is not what it should look like. So this is not good enough because, like I said, some of our clients want to use this kind of environment maps. So instead, you have a choice. You can use spherical harmonics, or you can use a diffuse map. So this is the same scene with diffuse lighting coming from a texture. This is much, much better. It's much closer to what you would get from an analytical directional light. Right, so diffuse map gives better result, but is this what we truly want? So an extra diffuse map will cost a sampler. We have a limit of 16 samplers on mobile, so we don't want that. It's also more memory, more storage. It's an extra texture you have to carry around. It makes things more complicated. So ultimately, we decided it was not worth it. But the insight was to use the specular map instead, or the pre-convolved environment map MIP chain. So if you squint hard enough at the equations, the integration of the specular BRDF at roughness 1 is very close to diffuse lighting. And since we already rely on approximations like the split sum approximation, what's one more approximation? So of course, this means that we don't want to use the 1x1 pixel LUD for the roughness for this diffuse map, because that would not be high resolution enough. So instead, we use the 16x16 MIP level, which means that we stop our MIP chain at 16x16 per face, and it looks good enough. So the same example we just saw earlier looks like this. Now, if you look at the terminator between the light and the shadowed part, you can see there is some aliasing. We can fix that using a tint filter. That's what we use on desktop. But in practice, the aliasing on mobile is not a big deal. Let me go back and forth. Because you're going to have textures, there's going to be like more interesting geometry. Chances are the effect is not going to be that visible. And you can always switch back to spherical harmonics if that really bothers you. So we want to use the specular level that holds a 16x16 MIP level as our diffuse map. And because we start at 256x256, that gives us only 5 MIP levels. So we have to find a good mapping for the roughness that maximizes the resolution of the low MIP levels for the glossy surfaces. So our empirical solution is the following mapping: the log2 of the roughness plus the index of the MIP level that contains the 16x16. In practice, we don't want to use log2 on mobile, so we use this quadratic fit instead. So really cheap, and it works. This mapping works really well up to at least 9 MIP levels. So you can use it with higher resolution cube maps if you want. So in practice, this is how the mapping works. You can see that the first four levels map to roughness between 0 and 0.25. So this is where things are sharp, where we want to maximize resolution, especially since trilinear filtering of the cube map doesn't look that great. Frankly, this was something that was bothering us with our previous mapping that was just the square of the roughness. And above 0.25, things become very blurry anyway, so it doesn't really matter if we lose details. And to convince you, so here's an example of a metallic sphere with the roughness varying from 0 to 1. And as you can see, the results look really good. So storing the IBL is a bit of an issue on mobile. They contain HDR data, and because we target ES3 devices, there's no good suitable compression formats for textures that store HDR data that's available on all devices. So we were initially using RGBM, but when we had to add support for those really high dynamic range environments, RGBM just didn't work anymore. We couldn't find a shared multiplier that worked across the range of dynamic range that we needed to support. So instead, we used a small float format, so R11, G11, B10F. We lose a bit of precision in the darks, but we can swizzle it as RGBA8, which means we can store it in PNG files. It can go easily in KTX. So as long as you don't apply another kind of lossy compression on top of it, it's going to look great. It's going to be easy to manage. You can even kind of look at it in image viewers. It's going to look weird, but you can make some sense of it. But another thing we did in filament was fix metals. So one thing that always bothered us is that with the Cook tolerance BRDF that we use and that many people use, only a single bounce of light is modeled in the macrofacet field. So that leads to a loss of energy at high roughness. So intuitively, it makes sense, right? If you look on the left, we model a single bounce in the field of macrofacet, so chances are it's going to be masked or shadowed. If you model multiple scattering events, as on the right, you have higher chances that it's going to reflect back towards the viewer. And when you implement that, you get the result at the bottom here. So you can see that this metallic ball, like this gold, retains its brightness and its saturation even at high roughness. It's even more obvious when we look at a white furnace. So there are two rows of sphere here. The top one is a single scattering event. You can see it's losing energy. And the bottom one retains reflects back all the energy as it should and behaves properly. So we use a solution from Lagarde and Golubev from Unity that they presented at SIGGRAPH 2018. And that solution goes like this. So you have a single scattering lobe, so that's your typical BRDF, and you just add a second multiple scattering lobe. The key insight they had was that the multi-scatter lobe is actually just a scaled version of the single scattering lobe. And the term R that shows up in this equation happens to be something we compute in the DFG lookup table for image-based lighting anyway. It's the integration of the distribution function and the visibility term over the hemisphere. So typically, the code that you use to generate your lookup table, your DFG lookup table will look something like this. So the visibility times the Fresnel. And we can modify it a little bit to have one of the terms contain only the visibility, the integration of visibility. And then it becomes really easy to plug that back into the shaders The image-based lighting code almost doesn't change. What's interesting is for the analytical lights, you first compute this energy compensation term that just follows the equation that we saw earlier. And once you have that, you can apply it as a multiplication to all the lights. So for the cost of 3 multiplies per light, you can fix your metals. We also apply it to the electrics. It is not really correct the way we do it, and the solution that we use contains approximations as explained by Lagarde and Golubev in their presentation, but definitely worth it given the cost. Cloth rendering. So we offer a cloth material model. You can see an example here of varying roughness. It is based on the Ashikmin BRDF as modified by Newbelt and Petineo for the order 1886, but we use a different distribution function. So we use the so-called Charlie Sheen distribution function term from Estevez and Kula from Sony ImageWorks that they presented at SIGGRAPH 2017. It is softer, cheaper, and provides a more natural control over the roughness, we feel. So however, because we use a different BRDF, we cannot use the DFG LUT as is. That LUT is computed for the regular Cook-Torrens BRDF, so it has a Fresnel term and a different distribution function. By the way, this is the single scattering LUT, just because you might be more used to that one, but our actual lookup table looks different because of the multiple scattering. So if you remember the equation on the previous slide, there is no Fresnel term in that BRDF. So the key here, that means that we only need to add one extra channel to our lookup table to store that extra BRDF. So here I have reference code. We'll publish the slide so you can look at it. But it looks very similar to what you would do for the regular lookup table. Of course, we should convolve the environment maps with that new BRDF. So we should, in theory, need a second set of IBLs, of MIP chains for that BRDF. But again, it's not practical in terms of storage, memory, performance on mobile. So we don't do that. We reuse what we already have. It is wrong, but it's good enough. Multi-band ambient occlusion. So the way ambient occlusion is usually computed is using a single visibility test. So thankfully, Jimenez offered a great solution at SIGGRAPH 2016 in practical real-time strategies for accurate indirect occlusion. And it looks like this. So this is a scene. It's not using screen shading, by the way, with ambient occlusion, like regular ambient occlusion. And look at the ear and around the nose and the eyes. And when I switch back and forth with the solution presented by Jimenez, this is what we get. So it's a little brighter, it's more colorful, it's more natural. Because their solution simulates bounces of light, it also simulates global illumination locally. So we can get some of the color back from the object itself. The implementation is just a polynomial fit. So it's extremely simple. It's really easy to implement, very easy to integrate in your renderer, and it's definitely worth having. It is optional in Filament. You have to enable it per material, but you might decide to turn it on all the time. We mostly use MSA and FXA because TA would be too complicated, first of all, to implement, and also it would impose constraints on our users. But so sometimes MSA and FXA are not enough, and we need more to anti-alias specular lighting. So here's an example. If you look at the statue just above the waist, there's kind of like a vertical highlight. And if we move away from the statue, you can see that the highlight gets lost. And even all the other highlights, the punctual highlights, disappear. And under motion, there will be a lot of shimmering. With specular anti-aliasing, we get this result instead. And as you can see, when we move around, we can retain the shape of the highlights, and everything looks a lot better and it's way more stable. So we use a solution devised by Anton Kaplanian in 2016. It was improved by Yusuke Toyushi in 2017, and they both together improved it again in 2019. So basically, you look at the variance of the geometric normal for the current pixel, and you change the roughness based on that. So the paper has two solutions, one for deferred rendering and one for forward rendering. Filament is a forward renderer, but that solution requires a multiplication by a tangent frame for every light. So we deemed it too expensive. So we used the deferred rendering solution in our forward renderer, and it works really well. And the cost is very often worth it. It's fairly cheap. It's a couple of dot products. We have a couple of derivatives, and there's a couple of square roots. But you do it only once since you modify the roughness. It is an optional feature, so you turn it on only for the materials that need it. All right, next up, ambient occlusion. So we use an algorithm called Scalable Ambient Obscurance by Morgan Maguire. And we chose it because it delivers really good quality, even with just a few samples. So in our low quality mode we use on mobile, it's only 7 samples. And it runs fast, so it's about 2 milliseconds at 1080p on a Pixel 4. And to generate this effect, we generate a chain of MIP maps for the depth that we can reuse for other effects, so we can amortize the cost of the ambient occlusion. For instance, we can reuse it for depth of field. To give you an idea, it looks like this. So on this scene, that's without ambient occlusion and with. So if I go back and forth, these really good results, and that's only with 7 samples, and that's with the low quality upsampler. But of course, we provide high quality settings if you want to use them. We've made a few changes to make it faster. We changed the noise to use an interleaved gradient noise. It's cheaper. The sampling pattern, originally, it's a spiral and it uses sines and cosines. Those are EFU instructions on Qualcomm GPUs, so they have higher latency and they use more power. So instead we use a constant, it's much cheaper. We don't reconstruct the normals from using derivatives because on mobile we only have partial derivatives on a lot of GPUs. And the code that we have instead that computes the normals at full resolution is just as fast as the derivatives anyway. And of course, we made the code friendly for half-floats. Then on the CPU side, we have our job system. So I'm going to use this scene as an example on Pixel 4. So this scene has about 45 lights. Some have shadows, some don't. But there's a lot of lights. It's a fairly complex scene, tons of triangle, lots of objects. There's hundreds of draw calls. So our job system is used everywhere in Filament. Every loop pretty much uses the job system for multi-threading. Our implementation is heavily influenced by the implementation from Autodesk Stingray that was described in their blog. And here are some of the results. So our render loop, which includes for multiple passes, the culling, the frustum culling, the sorting, what we call voxelization. So we have clustered forward rendering, so we have to assign the lights to voxels inside the frustum. Anyway, all of that takes 1.15 milliseconds, and we run on all the cores that we can find available, which is 8 cores on the Pixel 4. And in this scene, we end up with 200 visible objects, so that's 200 draw calls across multiple render passes. And that takes an extra 8 milliseconds or so on what we call the driver thread. So this is the thread on which we call OpenGL. So as you can see, like in Filament itself, we actually don't spend a lot of time. So here you can see the job system in action when we load the scene. Every ping block is a job in the job system. And we can see that we maximize occupancy. We use all 8 cores. We do reserve one of the cores for the render thread, for the driver, for making the OpenGL calls. What's very important here is that we pin our threads to specific cores. So for instance, the last one, the blue blocks at the bottom, that's our driver thread. We pin it to the big cores in the big little configuration because we know it's going to do a lot of work, and this one is single-threaded for GL. And even the job system, like every thread of the job system is pinned to a specific core. So here's what the code looks like. So this is the core loop of every thread. Every time a thread wakes up, we set the affinity again because on Android, the CPU can get unplugged for power reasons, and that resets the affinity. On the driver thread, we have a heuristic to try to pick a big core. And same thing, whenever the driver thread wakes up, before we execute the command queue, we set the affinity again. And this is what the code looks like on Android to set the affinity. It's pretty simple, and again, we'll release the slides, or you can go look at our source code. So that's pretty much it for today. I just wanted to add, so we did a lot of work to multi-thread Filament. We did other things as well. So for instance, we wrote our libmath in a way that's very compiler friendly so that without writing intrinsics, we get SIMD code. We have neon code for ARM64. There's a lot of interesting tips and tricks that we use in our source code to make that possible. For instance, sometimes we have to prevent unrolling of the loops, but we've seen Clang in particular as a compiler. We've seen it do amazing things like, 2 nested loops will be flipped inside out to better vectorize the implementation. We also do a lot of branchless code in our render loop. So our core render loop that generates all the drawing commands for the driver, for the depth passes, shadow passes, for the opaques, for the translucent. Some of the translucents have 2 passes themselves. So all that code is completely branchless, vectorized, multi-threaded, and this is why our render loop can be so fast on a mobile phone. So I really encourage you to go look at the source code of Filament on GitHub. There's a lot of interesting things. The main interesting parts of the code, like the render loop, are documented. And if you do have questions, you can reach me on Twitter. It's @Romangui. You can also, of course, ask questions on our GitHub. We will release the slides for this talk. We have all the references for the different papers and presentations that I mentioned during this presentation, so you can see them flash by on screen. And we also have links to all the assets that we use to create the different screenshots in the presentation. So that's it for me, and thank you so much for your time.
That was great. Again, thanks to all of our speakers. Thanks again to SIGGRAPH committee for having us, and thanks to all of you for attending. Again, all the contact info is on this slide, so feel free to check back for course notes or again to give us feedback. We'd really appreciate it. So hope you have a great rest of your SIGGRAPH, and take care, everybody.